Picture this: in the blink of an eye, a burst of energy brighter than 1 billion suns erupts in the far reaches of space. This is no ordinary explosion. It's a gamma-ray burst, one of the most powerful and mysterious events in the universe. These cosmic fireworks, born from the deaths of massive stars or the collisions of neutron stars, unleash more energy in seconds than our sun will produce in its entire lifetime. And the most astonishing part, some of these bursts come from the very edge of the observable universe, billions of light years away, offering us a glimpse into the cosmos as it was just moments after the Big Bang. Gamma-ray bursts are not just spectacular light shows. They are cosmic puzzles holding secrets about the birth of black holes, the formation of galaxies, and even the origins of the elements that make up everything around us. But what makes them truly fascinating is how little we still understand. Why do some bursts last mere milliseconds while others shine for minutes? What triggers these colossal explosions, and what can they tell us about the universe's most distant corners? In this video, we're diving deep into the mysteries of gamma-ray bursts, exploring 50 incredible facts about these distant cosmic phenomena. From their discovery by accident during the Cold War to their role in shaping the universe as we know it, we'll uncover the science, the history, and the unanswered questions that make gamma-ray bursts one of the most captivating topics in astrophysics. So, buckle up and get ready to journey to the farthest reaches of space and time, where the universe's most powerful explosions light up the darkness. Let's begin. Now, let's start with the basics. Gamma-ray bursts, often abbreviated as GRBs, are the most energetic explosions known to exist in the universe. These bursts are incredibly powerful, releasing more energy in just a few seconds than our sun will emit over its entire 10 billion-year lifespan. But what exactly causes these colossal outbursts? Most gamma-ray bursts originate from two main sources. The first is the collapse of massive stars, often referred to as hypernova, which occur when a star many times more massive than our sun exhausts its fuel and collapses under its own gravity, forming a black hole. The second source is the collision of two neutron stars, incredibly dense remnants of dead stars, which release a tremendous amount of energy when they merge. Detecting these bursts is no small feat. Gamma-ray bursts are so distant and fleeting that they require highly sensitive instruments to capture them. Satellites like NASA's Swift and Fermi are specifically designed to detect the initial burst of gamma rays, which are the highest energy form of light. Once a burst is detected, astronomers quickly turn their telescopes to the source to observe the afterglow, which appears in X-ray, optical, and radio wavelengths. This afterglow provides crucial clues about the burst's origin and the environment in which it occurred. So, why are gamma-ray bursts so significant in astrophysics? For one, they serve as cosmic flashlights, illuminating the distant universe and allowing us to study regions that would otherwise remain hidden. They also help us understand the life cycles of stars, the formation of black holes, and even the creation of heavy elements like gold and platinum. In many ways, gamma-ray bursts are like cosmic messengers, delivering insights into some of the most extreme and mysterious processes in the universe. As we move forward, we'll explore more about these fascinating phenomena, starting with how they were first discovered and the surprising story behind their detection. But for now, remember this: gamma-ray bursts are not just explosions. They are windows into the universe's most dramatic and transformative events. Now, let's take a step back in time to uncover how gamma-ray bursts were first discovered. It's a story that begins not with astronomers peering through telescopes, but with military satellites designed for an entirely different purpose. In the 1960s, during the height of the Cold War, the United States launched a series of satellites called Vela. These satellites were tasked with monitoring the Earth for nuclear explosions, ensuring compliance with international treaties. But instead of detecting man-made explosions, they stumbled upon something far more mysterious: gamma-ray bursts coming from deep space. At first, scientists were baffled. The bursts appeared randomly, lasting only a few seconds, and seemed to come from all directions. The initial assumption was that these signals might be related to nuclear tests or some form of secret military activity. But as more data came in, it became clear that these bursts were not of earthly origin. They were cosmic, and their source was millions, if not billions, of light years away. This accidental discovery marked the beginning of a new era in astrophysics, one that would challenge our understanding of the universe. The confusion surrounding gamma-ray bursts didn't end with their detection. For decades, scientists debated what could possibly produce such immense energy in such a short time. Were they coming from within our galaxy, or were they originating from the far reaches of the universe? The breakthrough came in the 1990s when satellites like NASA's Compton Gamma-ray Observatory provided more precise data. These observations revealed that gamma-ray bursts were not only incredibly distant, but also associated with some of the most violent events in the cosmos, such as the collapse of massive stars and the mergers of neutron stars. This discovery transformed gamma-ray bursts from a puzzling anomaly into one of the most important tools for studying the universe. They became cosmic beacons, allowing scientists to probe the early universe, test the laws of physics, and even measure the expansion of space itself. What started as an accidental detection by military satellites has since opened a window into the most extreme and energetic processes in the cosmos. As we continue, we'll dive deeper into the two main types of gamma-ray bursts and how they differ in their origins and characteristics. But for now, let's appreciate the serendipity of their discovery, a reminder that sometimes the most profound scientific breakthroughs come from the most unexpected places. Now that we've explored the accidental discovery of gamma-ray bursts, let's turn our attention to the two distinct types that scientists have identified. Gamma-ray bursts are not all the same. They come in two main flavors, each with its own unique characteristics and origins. The first type is known as short-duration gamma-ray bursts. These bursts are incredibly brief, lasting less than 2 seconds. Despite their fleeting nature, they pack an extraordinary punch, releasing immense amounts of energy in that short window. Scientists believe these short bursts are linked to the violent collisions of neutron stars, the incredibly dense remnants of massive stars that have exploded in supernova. When two neutron stars spiral toward each other and merge, they unleash a torrent of gamma rays, gravitational waves, and other high-energy emissions, creating one of the most spectacular events in the universe. On the other hand, we have long-duration gamma-ray bursts which last more than 2 seconds and can sometimes persist for several minutes. These bursts are thought to originate from the collapse of massive stars, often referred to as hypernova. When a star many times more massive than our Sun exhausts its fuel, its core collapses under its own gravity, forming a black hole. In the process, jets of material are launched at nearly the speed of light, producing a gamma-ray burst that can outshine entire galaxies. These long bursts are often accompanied by supernova, making them a key tool for studying the life cycles of stars and the formation of black holes. While both types of gamma-ray bursts are incredibly energetic, their differences in duration and origin provide valuable insights into the diverse processes at work in the universe. Short bursts offer a glimpse into the violent mergers of neutron stars, while long bursts reveal the dramatic deaths of massive stars. Together, they paint a vivid picture of the extreme and dynamic nature of our cosmos. As we move forward, we'll explore how these bursts are detected and what they tell us about the universe's most distant and mysterious phenomena. But for now, let's marvel at the fact that these fleeting flashes of light, lasting mere seconds or minutes, can reveal so much about the universe's most powerful events. Now that we've explored the two main types of gamma-ray bursts, let's take a closer look at the fascinating science behind short-duration bursts and their connection to neutron stars. These cosmic powerhouses play a starring role in some of the most explosive events in the universe. Short gamma-ray bursts lasting less than 2 seconds are thought to originate from the violent mergers of neutron stars. These incredibly dense objects, born from the remnants of massive stars that have exploded in supernova, are so compact that a single teaspoon of neutron star material would weigh billions of tons on Earth. When two neutron stars spiral toward each other, their immense gravitational pull causes them to collide in a cataclysmic event. This collision doesn't just produce a burst of gamma rays, it also sends ripples through the fabric of spacetime known as gravitational waves. These waves, first predicted by Albert Einstein over a century ago, were directly detected for the first time in 2015, marking a monumental breakthrough in astrophysics. The merger of neutron stars not only generates gravitational waves but also launches jets of material at nearly the speed of light, creating the intense gamma-ray bursts we observe. What makes these events even more remarkable is that they are cosmic factories for heavy elements like gold and platinum. The extreme conditions during the merger forge these precious metals, which are then scattered into space, eventually becoming part of new stars, planets, and even life itself. This means that the gold in your jewelry or the platinum in your electronics may have originated from the collision of neutron stars billions of years ago. By studying short gamma-ray bursts and their connection to neutron star mergers, scientists gain invaluable insights into the behavior of matter under extreme conditions, the nature of gravity, and the origins of the universe's heaviest elements. These fleeting flashes of light, lasting mere seconds, open a window into some of the most violent and transformative events in the cosmos. As we continue our journey through the mysteries of gamma-ray bursts, we'll next explore how long-duration bursts are linked to the dramatic deaths of massive stars and the birth of black holes. But for now, let's marvel at the incredible role neutron stars play in shaping the universe, one explosive collision at a time. Now, let's shift our focus to the other side of the gamma-ray burst spectrum, long-duration bursts. These cosmic explosions, lasting more than 2 seconds, are deeply connected to the dramatic deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support its own weight. The core collapses under its immense gravity, triggering a catastrophic explosion known as a supernova. But in some cases, this isn't the end of the story. For the most massive stars, the collapse doesn't stop at a supernova. Instead, the core continues to implode, forming a black hole. As this happens, jets of material are launched outward at nearly the speed of light, piercing through the outer layers of the dying star. These jets, incredibly focused and energetic, produce the long gamma-ray bursts we observe. The sheer power of these events is staggering. In just a few seconds, they can release more energy than our Sun will emit over its entire 10 billion-year lifetime. What makes long gamma-ray bursts particularly fascinating is their role as cosmic beacons. Because they are so bright, they can be seen across vast distances, allowing astronomers to study the early universe. In fact, some of the most distant gamma-ray bursts ever detected are long-duration bursts, offering a glimpse into the era when the first stars and galaxies were forming. But the story doesn't end with the burst itself. The aftermath of these explosions is equally intriguing. As the jets interact with the surrounding material, they produce a glowing afterglow that can be observed in X-rays, visible light, and radio waves. This afterglow provides crucial clues about the environment of the explosion and the nature of the star that caused it. By studying long gamma-ray bursts and their connection to supernova, scientists gain insights into the life cycles of the most massive stars, the formation of black holes, and the conditions in the early universe. These explosive events remind us that even in death, stars can illuminate the cosmos in extraordinary ways. As we continue our exploration, we'll next turn our attention to the most distant gamma-ray burst ever detected, a record-breaking event that takes us to the edge of the observable universe. But for now, let's reflect on the incredible power of supernova and the black holes they leave behind, shaping the universe one explosion at a time. Now, let's journey to the farthest reaches of the cosmos, where we encounter the most distant gamma-ray burst ever detected, GRB 090423. This extraordinary event occurred an astonishing 13 billion light-years away, making it a true time capsule from the early universe. To put that into perspective, this burst happened when the universe was just a fraction of its current age, a mere 600 million years old. The detection of GRB 090423 was a monumental achievement for astronomers. Using the SWIFT satellite, scientists were able to pinpoint the burst's location and measure its incredible distance. What makes this discovery so significant is that it offers a rare window into the universe's infancy, a time when the first stars and galaxies were beginning to form. Gamma-ray bursts like this one act as cosmic flashlights, illuminating the distant reaches of space and time. By studying the light from GRB 090423, researchers gained valuable insights into the conditions of the early universe. They were able to analyze the composition of the gas and dust that existed billions of years ago, shedding light on the processes that shaped the cosmos as we know it today. This distant burst also provided clues about the nature of the stars that produced it. The energy and duration of GRB 090423 suggested originated from the collapse of a massive star, similar to the long-duration bursts we discussed earlier. However, the extreme distance means this star lived and died in an era when the universe was vastly different from what we see today. The discovery of GRB 090423 not only pushed the boundaries of our observational capabilities, but also deepened our understanding of the universe's history. It serves as a reminder that even the most fleeting cosmic events can leave a lasting impact, offering us a glimpse into the distant past and the origins of everything we see around us. As we continue our exploration, we'll next delve into the incredible speed at which gamma-ray bursts travel, a phenomenon that challenges our understanding of physics and the limits of the universe. But for now, let's marvel at the fact that we can observe events so far away, bridging the gap between the ancient cosmos and our modern quest for knowledge. Now, shifting our focus to the sheer velocity of these cosmic phenomena, let's explore the breathtaking speed at which gamma-ray bursts travel. These bursts move at nearly the speed of light, a staggering 300,000 kilometers per second. To put that into perspective, if you could travel at this speed, you could circle the Earth 7.5 times in just 1 second. This incredible velocity is one of the defining characteristics of gamma-ray bursts, making them some of the fastest-moving events in the universe. The speed of gamma-ray bursts presents both opportunities and challenges for astronomers. On one hand, their rapid movement allows them to traverse vast cosmic distances in a relatively short amount of time, bringing us information from the farthest corners of the universe. On the other hand, this speed also means that gamma-ray bursts are fleeting events, often lasting only a few seconds. Detecting and studying them requires precise timing and advanced technology, as even a slight delay can mean missing the burst entirely. One of the biggest challenges posed by their speed is the difficulty in pinpointing their exact origins. Because gamma-ray bursts travel so quickly, their light can be distorted or delayed by the vast expanses of space they traverse. This distortion, known as time dilation, occurs due to the immense distances and the expansion of the universe. As a result, astronomers must account for these effects when analyzing the data, adding layers of complexity to their observations. Despite these challenges, the speed of gamma-ray bursts also provides valuable insights into the nature of the universe. By studying how these bursts interact with the space they travel through, scientists can learn more about the structure of the cosmos, including the distribution of matter and the behavior of light over vast distances. Additionally, the speed of gamma-ray bursts helps researchers test the limits of our understanding of physics, particularly the theory of relativity, which predicts how objects behave at such extreme velocities. As we continue to unravel the mysteries of gamma-ray bursts, their incredible speed remains a key area of fascination and study. It's a reminder of just how dynamic and fast-paced the universe can be, even on the grandest scales. Next, we'll dive into the staggering energy output of these bursts, exploring how they can outshine entire galaxies in a fraction of a second. But for now, let's take a moment to appreciate the sheer velocity of these cosmic explosions, a testament to the universe's boundless energy and motion. Now, let's turn our attention to the mind-blowing energy output of gamma-ray bursts. These cosmic explosions are not just fast, they're also unimaginably powerful. In fact, a single gamma-ray burst can release more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. To put that into perspective, imagine the Sun's energy output condensed into a fraction of a second. That's the kind of raw power we're talking about here. What makes this even more astonishing is that gamma-ray bursts can outshine entire galaxies, even if only for a brief moment. Picture this: a galaxy like our Milky Way contains hundreds of billions of stars, each emitting light and energy. Yet, during a gamma-ray burst, the energy released can dwarf the combined light of all those stars. It's like a cosmic fireworks display on a scale that's almost impossible to comprehend. But where does all this energy come from? For long-duration gamma-ray bursts, the energy is often linked to the collapse of massive stars into black holes. As the star's core collapses, it releases an enormous amount of energy in the form of jets that shoot out at nearly the speed of light. These jets are what we detect as gamma-ray bursts. For short-duration bursts, the energy is typically produced by the collision of neutron stars, which also results in a massive release of energy in a very short time. To give you a sense of just how extreme this energy output is, let's compare it to some other cosmic events. A supernova, which is the explosive death of a star, is one of the most energetic events in the universe. Yet, a gamma-ray burst can release up to 100 times more energy than a supernova. Even the most powerful quasars, which are supermassive black holes devouring matter at the centers of galaxies, pale in comparison to the sheer intensity of a gamma-ray burst. This incredible energy output isn't just a spectacle, it's also a valuable tool for scientists. By studying the energy released during gamma-ray bursts, researchers can learn more about the processes that drive these events, such as the formation of black holes and the behavior of matter under extreme conditions. It also helps astronomers probe the distant universe, as the light from these bursts can travel billions of light years to reach us, carrying information about the early cosmos. As we marvel at the sheer power of gamma-ray bursts, it's worth reflecting on what they tell us about the universe. These events remind us that the cosmos is a place of extremes, where energy and matter interact in ways that push the boundaries of our understanding. Next, we'll explore the afterglow of gamma-ray bursts, the lingering light that follows these explosive events and provides even more clues about their origins. But for now, let's take a moment to appreciate the staggering energy of gamma-ray bursts, a testament to the universe's capacity for both creation and destruction on an unimaginable scale. Now, let's shift our focus to what happens after the initial explosion, the afterglow of gamma-ray bursts. While the burst itself lasts only a few seconds, the afterglow can persist for days, weeks, or even months, shining in X-ray, optical, and radio wavelengths. This lingering light is like the cosmic echo of the explosion, offering scientists a treasure trove of information about the event. The afterglow is created when the high-speed jets from the gamma-ray burst collide with the surrounding interstellar gas and dust. This collision generates shock waves that heat up the material, causing it to emit light across multiple wavelengths. Think of it as the universe's way of leaving behind a glowing trail, marking the path of the burst's energy as it travels through space. One of the most fascinating aspects of the afterglow is how it helps astronomers pinpoint the location of the gamma-ray burst. The initial burst is often so brief and intense that it's difficult to determine exactly where it came from. But the afterglow, with its longer-lasting emissions, allows telescopes to zero in on the source. This is crucial for understanding the environment where the burst occurred, whether it's in a distant galaxy or a region of active star formation. The afterglow also provides clues about the physics of the burst itself. By studying how the light fades over time, scientists can learn about the energy and speed of the jets, as well as the properties of the surrounding material. For example, a rapidly fading afterglow might indicate that the jets are narrow and highly focused, while a slower fade could suggest a wider spread of energy. Perhaps most importantly, the afterglow helps researchers probe the distant universe. Because gamma-ray bursts are so bright, their afterglows can be seen across vast cosmic distances. This makes them invaluable tools for studying the early universe, as the light from these events carries information about the conditions billions of years ago. It's like having a time machine that lets us glimpse the universe in its infancy. As we explore the afterglow, it's clear that this phenomenon is more than just a cosmic afterthought. It's a vital piece of the puzzle, helping scientists unravel the mysteries of gamma-ray bursts and the universe itself. Next, we'll dive into the role of satellites in detecting these bursts, shedding light on the technology that makes these discoveries possible. But for now, let's marvel at the afterglow, a glowing testament to the enduring power of these cosmic explosions. Now, let's turn our attention to the unsung heroes of gamma-ray burst detection satellites. Without these high-tech observatories orbiting Earth, much of what we know about these cosmic explosions would remain a mystery. Satellites like NASA, Swift, and Fermi have revolutionized our ability to detect, study, and understand gamma-ray bursts, acting as our eyes in the sky for these fleeting yet powerful events. The Swift satellite, launched in 2004, is specifically designed to catch gamma-ray bursts in the act. Its name stands for Swift Gamma-Ray Burst Mission, and it lives up to its title by being incredibly fast. When Swift detects a burst, it can quickly swivel its instruments to observe the event in multiple wavelengths, from gamma rays to X-rays and even visible light. This rapid response is crucial because gamma-ray bursts are so short-lived. Swift's ability to pinpoint the location of a burst within seconds allows ground-based telescopes to follow up almost immediately, capturing valuable data about the afterglow and the burst's environment. Then there's the Fermi Gamma-Ray Space Telescope, launched in 2008, which takes a broader approach. Fermi is equipped with instruments that can detect gamma rays across a wide range of energies, giving scientists a more comprehensive view of these explosions. One of Fermi's key contributions is its ability to detect the highest energy gamma rays ever observed from gamma-ray bursts. These observations have provided new insights into the extreme physics at play, such as how particles are accelerated to nearly the speed of light within the burst jets. Together, Swift and Fermi have transformed our understanding of gamma-ray bursts. They've helped us map the distribution of these events across the universe, revealing that they occur in all types of galaxies and at all cosmic distances. They've also provided critical data on the two main types of burst, short and long, helping scientists confirm their different origins, such as neutron star mergers for short bursts and supernova for long bursts. But the contributions of these satellites go beyond just detection. They've also played a key role in multi-messenger astronomy, where observations of gamma-ray bursts are combined with data from other sources like gravitational wave detectors. For example, in 2017, Fermi and Swift were instrumental in linking a gamma-ray burst to the collision of two neutron stars, an event that also produced gravitational waves. This groundbreaking discovery marked the beginning of a new era in astronomy, where we can study cosmic events using multiple messengers like light and gravitational waves. In essence, satellites like Swift and Fermi are more than just tools, they're our partners in unraveling the mysteries of the universe. By capturing the fleeting brilliance of gamma-ray bursts, they've opened a window into some of the most energetic and enigmatic events in the cosmos. Next, we'll explore how these bursts are connected to one of the universe's most fascinating objects, black holes. But for now, let's take a moment to appreciate the incredible technology that makes these discoveries possible, bringing the distant universe closer to us than ever before. Now, let's dive into one of the most intriguing aspects of gamma-ray bursts, their deep connection to black holes. Gamma-ray bursts are not just random explosions in the cosmos. They are often the birth cries of black holes, some of the most mysterious and powerful objects in the universe. This connection is not only fascinating but also sheds light on the life cycles of massive stars and the extreme physics that govern these cosmic events. When a massive star reaches the end of its life, it doesn't go quietly. Instead, it collapses under its own gravity in a cataclysmic explosion known as a supernova. For the most massive stars, this collapse doesn't stop at forming a neutron star. It continues until the core is crushed into a black hole. This process releases an enormous amount of energy, which is channeled into narrow jets of particles and radiation that shoot out at nearly the speed of light. These jets are what we observe as gamma-ray bursts. In essence, a gamma-ray burst is like a cosmic beacon signaling the birth of a black hole. But the connection doesn't end there. Short gamma-ray bursts, which last less than 2 seconds, are also linked to black holes, but in a different way. These bursts are thought to occur when two neutron stars collide and merge. The merger creates a black hole almost instantly, accompanied by a burst of gamma rays. This process not only produces gamma-ray bursts but also generates gravitational waves, ripples in spacetime that were first detected in 2015. The detection of both gamma rays and gravitational waves from the same event has provided some of the strongest evidence for this connection, marking a major milestone in astrophysics. The implications of this link between gamma-ray bursts and black holes are profound. For one, it helps us understand how black holes form and grow. By studying gamma-ray bursts, scientists can piece together the conditions that lead to the creation of these enigmatic objects. Additionally, gamma-ray bursts serve as natural laboratories for testing the laws of physics under extreme conditions. The intense energy and magnetic fields involved in these events push our understanding of particle acceleration, jet formation, and even the nature of spacetime itself. Moreover, gamma-ray bursts provide a unique way to study black holes across vast cosmic distances. Because these bursts are so bright, they can be seen from the farthest reaches of the universe, offering a glimpse into the early stages of black hole formation. This makes them invaluable tools for probing the evolution of the universe and the role black holes play in shaping galaxies. In summary, gamma-ray bursts and black holes are deeply intertwined, with these explosive events often marking the birth or transformation of black holes. This connection not only enriches our understanding of these cosmic phenomena, but also opens new avenues for exploring the fundamental laws of physics. Next, we'll uncover another layer of mystery surrounding gamma-ray bursts, those that leave no visible trace, known as dark gamma-ray bursts. But for now, let's marvel at how these fleeting flashes of light reveal the hidden workings of the universe's most enigmatic objects. Now, let's turn our attention to a puzzling phenomenon in the world of gamma-ray bursts, dark gamma-ray bursts. Unlike their more visible counterparts, these bursts leave no trace of an afterglow in optical light, making them incredibly challenging to detect and study. This absence of visible light has led scientists to dub them dark GRBs, and their mystery has sparked intense curiosity and debate in the astrophysics community. So, what makes dark GRBs so elusive? The answer lies in their afterglows, or rather, the lack of them. After a typical gamma-ray burst, the initial explosion is followed by a fading glow of light across various wavelengths, including X-rays, optical light, and radio waves. This afterglow helps astronomers pinpoint the burst's location and study its properties. But with dark GRBs, this optical afterglow is either extremely faint or completely absent, leaving scientists with only the gamma-ray signal to work with. One leading theory suggests that dark GRBs occur in regions of space filled with dense clouds of dust. When the burst light passes through these clouds, the dust absorbs much of the optical light, effectively hiding the afterglow from our telescopes. Another possibility is that dark GRBs are simply located much farther away than we can currently observe, making their afterglows too faint to detect with existing instruments. In some cases, the jets of gamma rays might be pointed away from Earth, reducing the amount of visible light we can see. Studying dark GRBs is no easy task. Without the afterglow, astronomers must rely on other methods to locate and analyze these bursts. Satellites like NASA's Swift and Fermi play a crucial role in detecting the initial gamma-ray signal, but follow-up observations often require more advanced tools. Radio telescopes, for example, can sometimes detect faint afterglows in radio wavelengths, even when optical light is missing. Additionally, infrared observations have proven useful in piercing through the dust that might obscure the afterglow. The mystery of dark GRBs isn't just a scientific curiosity, it has broader implications for our understanding of the universe. These bursts could be hiding clues about the environments in which they occur, such as the presence of massive dust clouds or the conditions in the early universe. They also challenge our assumptions about gamma-ray bursts and push us to develop new techniques and technologies to study them. As we continue to unravel the secrets of dark GRBs, one thing is clear: these enigmatic events remind us just how much we still have to learn about the cosmos. Next, we'll explore another fascinating aspect of gamma-ray bursts: the role of magnetic fields in shaping these powerful jets of energy. But for now, let's reflect on how even the absence of light can illuminate some of the universe's deepest mysteries. Now, let's shift our focus to another key player in the drama of gamma-ray bursts: magnetic fields. These invisible forces are not just background actors, they are central to shaping the powerful jets of energy that define gamma-ray bursts. Without magnetic fields, these cosmic explosions might look very different, and understanding their role is essential to unraveling the mysteries of GRBs. Magnetic fields are like the architects of gamma-ray bursts, guiding and focusing the explosive energy into narrow, high-speed jets. When a massive star collapses or two neutron stars merge, the resulting explosion generates incredibly strong magnetic fields. These fields channel the energy outward in tightly collimated beams, creating the intense jets we observe as gamma-ray bursts. Without this magnetic influence, the energy would spread out in all directions, diluting the burst's power and making it far less detectable. But studying these magnetic fields is no simple task. Unlike the light from a GRB, magnetic fields are invisible and can only be inferred indirectly. Scientists rely on the behavior of the jets and the afterglow to piece together clues about the strength and structure of these fields. For example, the polarization of light in the afterglow can reveal information about the magnetic field's orientation and intensity. However, this requires precise measurements and advanced instruments, making it a challenging area of research. One of the biggest mysteries is how these magnetic fields are generated and maintained during a gamma-ray burst. Some theories suggest that the fields are amplified by the rapid rotation of the collapsing star or the merging neutron stars. Others propose that turbulence in the explosion plays a key role in creating and sustaining these fields. Whatever the mechanism, the result is a magnetic environment so extreme that it defies our everyday understanding of physics. The impact of magnetic fields on GRB behavior is profound. They not only shape the jets but also influence how the energy is released and how the afterglow evolves. For instance, magnetic fields can accelerate particles to nearly the speed of light, producing the high-energy gamma rays we detect. They can also affect the cooling of the jets, determining how long the afterglow lasts and in what wavelengths it appears. Despite the challenges, studying magnetic fields in gamma-ray bursts offers a unique window into some of the most extreme conditions in the universe. These fields are a testament to the incredible forces at work in cosmic explosions, and they push the boundaries of our understanding of physics. As we continue to explore their role, we gain not only insights into GRBs, but also a deeper appreciation for the complex interplay of forces that shape the cosmos. Next, we'll delve into another intriguing aspect of gamma-ray bursts, their potential impact on Earth and the rare but fascinating scenarios that could arise if one occurred nearby. But for now, let's marvel at how something as intangible as a magnetic field can wield such immense power in the universe. Now, let's turn our attention to a scenario that sounds like it belongs in a science fiction movie but is grounded in real science: the potential impact of a gamma-ray burst on Earth. While these cosmic explosions are incredibly rare, their effects, if one were to occur nearby, could be catastrophic. Imagine a burst so powerful that it could outshine the entire galaxy for a brief moment, releasing energy equivalent to billions of suns. If such an event happened within a few thousand light-years of Earth, the consequences would be nothing short of devastating. The most immediate threat from a nearby gamma-ray burst would be its intense radiation. The burst would bombard Earth with high-energy gamma rays, X-rays, and ultraviolet light, stripping away the ozone layer that protects us from the sun's harmful ultraviolet radiation. Without this protective shield, life on Earth would be exposed to dangerous levels of UV radiation, leading to widespread damage to ecosystems, crops, and even human health. The effects could trigger a cascade of environmental disasters, from mass extinctions to the collapse of food chains, but the damage wouldn't stop there. The burst's radiation could also ionize the atmosphere, creating a surge of charged particles that disrupt global communication systems, satellites, and power grids. Imagine a world plunged into darkness with no electricity, no internet, and no way to communicate across long distances. The societal and economic impacts would be unimaginable, potentially setting humanity back decades or even centuries. Despite these terrifying possibilities, it's important to note that the likelihood of a gamma-ray burst occurring close enough to Earth to cause such devastation is extremely low. GRBs are rare events, and the universe is vast. The closest known gamma-ray burst to Earth occurred over 2 billion years ago, and even then, its effects were negligible. However, the fact that such an event is possible reminds us of the unpredictable and often violent nature of the cosmos. Scientists continue to study gamma-ray bursts not only to understand their origins, but also to assess the risks they might pose to life on Earth. By monitoring the skies and improving our detection capabilities, we can better prepare for the unlikely but not impossible scenario of a nearby GRB. For now, though, we can take comfort in the fact that the odds are heavily in our favor, allowing us to marvel at these cosmic explosions from a safe distance. Next, we'll explore how gamma-ray bursts contribute to the evolution of the universe, shaping the cosmos in ways that go far beyond their explosive beginnings. But for now, let's reflect on the delicate balance that allows life to thrive on Earth, even in a universe filled with such immense and unpredictable forces. Shifting our focus from the potential dangers of gamma-ray bursts, let's now explore how these cosmic explosions play a vital role in shaping the universe itself. Gamma-ray bursts are not just destructive forces, they are also cosmic architects contributing to the evolution of the universe in profound ways. One of their most significant roles lies in the creation and dispersal of heavy elements, the building blocks of planets, stars, and even life as we know it. When a gamma-ray burst occurs, particularly those associated with the collapse of massive stars, it releases an immense amount of energy and matter into space. This matter includes heavy elements like gold, platinum, and uranium, forged in the extreme conditions of the star's core and supernova explosion. These elements are then scattered across vast distances, seeding the cosmos with the raw materials needed for future star and planet formation. Without gamma-ray bursts, the universe would lack many of the elements essential for the formation of complex structures, including the very atoms that make up our bodies. But the influence of gamma-ray bursts doesn't stop there. These explosive events also play a crucial role in triggering star formation. When the shock waves from a gamma-ray burst travel through interstellar gas clouds, they compress the gas, creating dense regions where new stars can begin to form. In this way, gamma-ray bursts act as cosmic catalysts, setting off a chain reaction of star birth that shapes the structure of galaxies over billions of years. It's a fascinating cycle: destruction giving rise to creation, and chaos paving the way for new beginnings. Moreover, gamma-ray bursts help regulate the chemical composition of galaxies. By dispersing heavy elements and influencing the conditions of star-forming regions, they ensure that galaxies evolve in a dynamic and balanced way. This process is essential for the diversity of stars and planetary systems we observe today, from massive blue giants to small, rocky worlds like Earth. In a sense, gamma-ray bursts are the universe's way of recycling and redistributing its resources, ensuring that the cosmos remains a vibrant and ever-changing place. As we continue to study these extraordinary events, we gain a deeper understanding of how they shape the universe on both large and small scales. From the creation of heavy elements to the birth of new stars, gamma-ray bursts are a testament to the interconnectedness of cosmic processes. Next, we'll dive into how gamma-ray bursts are detected not only in gamma rays but also across multiple wavelengths, revealing even more about their nature and impact. But for now, let's marvel at the dual role of these cosmic explosions, destroyers and creators, shaping the universe in ways we are only beginning to comprehend. Now, let's turn our attention to how gamma-ray bursts reveal their secrets across the entire electromagnetic spectrum. While gamma rays are the most energetic and defining feature of these cosmic explosions, they are just one piece of the puzzle. Gamma-ray bursts also emit energy in X-rays, optical light, and even radio waves, creating a multi-wavelength fingerprint that helps scientists unravel their mysteries. When a gamma-ray burst occurs, the initial flash of gamma rays is often followed by an afterglow that spans a wide range of wavelengths. This afterglow can last for hours, days, or even weeks, providing astronomers with a wealth of information. X-ray observations, for example, allow researchers to study the high-energy processes occurring in the aftermath of the burst, such as the interaction of shock waves with surrounding material. These observations help pinpoint the location of the burst and provide clues about its environment. Optical light, on the other hand, offers a different perspective. By studying the visible light emitted during the afterglow, scientists can measure the distance to the burst and gather details about the host galaxy. This is particularly important for understanding how gamma-ray bursts are distributed across the universe and what types of galaxies are most likely to produce them. Optical observations also help identify the remnants of the progenitor star, such as a supernova, which is often associated with long-duration bursts. Radio waves add yet another layer of insight. While radio emissions are less energetic than gamma rays or X-rays, they are incredibly useful for studying the long-term behavior of gamma-ray bursts. Radio observations can reveal how the burst interacts with the interstellar medium, the gas and dust that fill the space between stars. This helps astronomers map the structure of the jets produced by the burst and understand how they evolve over time. The importance of multi-wavelength observations cannot be overstated. By combining data from gamma rays, X-rays, optical light, and radio waves, scientists can build a comprehensive picture of these extraordinary events. Each wavelength provides a unique piece of the puzzle, and together they reveal the full story of a gamma-ray burst from its explosive birth to its lingering aftermath. This multi-wavelength approach has revolutionized our understanding of gamma-ray bursts, turning them from fleeting flashes of light into rich sources of cosmic knowledge. As we continue to explore the universe's most distant gamma-ray bursts, this ability to observe them across multiple wavelengths will remain a cornerstone of our research. Next, we'll delve into how gamma-ray bursts serve as cosmic yardsticks, helping astronomers measure distances across the vast expanse of the universe. But for now, let's appreciate the incredible power of multi-wavelength astronomy, which allows us to see these cosmic explosions in all their dazzling complexity. Now, let's shift our focus to how gamma-ray bursts act as cosmic yardsticks, helping astronomers measure vast distances across the universe. These powerful explosions are not just fleeting flashes of light, they are also invaluable tools for mapping the cosmos. Because gamma-ray bursts are so incredibly bright, they can be detected from billions of light-years away, making them ideal markers for measuring the scale of the universe. One of the key ways astronomers use gamma-ray bursts to measure distances is by analyzing their afterglows. As we've discussed, the afterglow emits light across multiple wavelengths, including optical and X-ray. By studying the brightness and behavior of this light, scientists can determine how far away the burst occurred. This method relies on a principle called the standard candle approach, where the intrinsic brightness of an object is compared to its observed brightness to calculate its distance. Gamma-ray bursts, with their extreme luminosity, serve as some of the most distant standard candles ever observed. However, using gamma-ray bursts as cosmic yardsticks isn't without its challenges. One major hurdle is the variability in their brightness. Unlike supernova, which have a more predictable luminosity, gamma-ray bursts can vary widely in energy output. This makes it difficult to establish a consistent baseline for distance measurements. To overcome this, astronomers have developed sophisticated models that account for the unique properties of each burst, such as its duration, energy, and the characteristics of its afterglow. These models help refine distance calculations and improve their accuracy. Another breakthrough in this field came with the discovery of a relationship between the peak energy of a gamma-ray burst and its total energy output. This correlation, known as the Amati relation, provides a way to estimate the intrinsic brightness of a burst based on its observed properties. By applying this relationship, scientists can more accurately determine the distance to gamma-ray bursts, even those located in the farthest reaches of the universe. The ability to measure cosmic distances using gamma-ray bursts has profound implications for our understanding of the universe. It allows astronomers to map the large-scale structure of the cosmos, study the expansion rate of the universe, and even probe the nature of dark energy. These bursts act as cosmic beacons, illuminating the vast distances between galaxies and helping us piece together the history and evolution of the universe. As we continue to refine our techniques for measuring distances with gamma-ray bursts, these extraordinary events will remain at the forefront of cosmological research. Next, we'll explore how gamma-ray bursts are linked to regions of active star formation, shedding light on the birth of new stars and the evolution of galaxies. But for now, let's marvel at the incredible role these bursts play in helping us measure the unimaginable scale of the cosmos. Now, let's turn our attention to the fascinating connection between gamma-ray bursts and the birth of new stars. These cosmic explosions are not just random events, they often occur in regions of the universe where stars are being born at an incredible rate. This link provides astronomers with a unique window into the processes that shape galaxies and drive the evolution of the cosmos. Gamma-ray bursts are frequently found in galaxies that are undergoing intense star formation. These galaxies, often referred to as starburst galaxies, are bustling with activity as massive clouds of gas and dust collapse under gravity to form new stars. The most powerful gamma-ray bursts, particularly the long-duration ones, are closely tied to the deaths of massive stars, which are born in these same star-forming regions. When these stars exhaust their fuel and collapse, they trigger supernova and, in some cases, gamma-ray bursts, marking both the end of their lives and the beginning of new cosmic cycles. But how exactly do gamma-ray bursts signal the birth of new stars? One key clue lies in their afterglows. As we've discussed, the afterglow of a gamma-ray burst emits light across multiple wavelengths, including X-ray, optical, and radio. By studying these emissions, astronomers can identify the host galaxy of the burst and determine whether it's a site of active star formation. Often, these galaxies are rich in young, hot stars and glowing clouds of ionized gas, all hallmarks of a stellar nursery. Moreover, gamma-ray bursts can act as cosmic probes, illuminating the environments in which they occur. The intense radiation from a burst can interact with the surrounding gas and dust, revealing details about the composition and density of these star-forming regions. This information helps scientists understand the conditions necessary for star formation and how these processes vary across different galaxies. Interestingly, the presence of gamma-ray bursts in star-forming regions also suggests a connection between the birth of stars and the formation of black holes. Many long-duration gamma-ray bursts are thought to result from the collapse of massive stars into black holes, a process that often occurs in the same regions where new stars are being born. This interplay between star formation and black hole creation highlights the dynamic and interconnected nature of the universe. As we continue to study gamma-ray bursts and their connection to star formation, we gain deeper insights into the life cycles of stars and the evolution of galaxies. These bursts serve as cosmic signposts, pointing us toward the most active and energetic regions of the universe. Next, we'll delve into how gamma-ray bursts provide a unique opportunity to test Einstein's theory of relativity, pushing the boundaries of our understanding of physics. But for now, let's appreciate the incredible role these bursts play in revealing the birthplaces of stars and the ongoing story of cosmic creation. Now, let's shift our focus to an extraordinary aspect of gamma-ray bursts: their role in testing one of the most fundamental theories in physics, Einstein's theory of relativity. These cosmic explosions, with their immense energy and incredible speeds, offer scientists a natural laboratory to explore the limits of our understanding of space, time, and gravity. Gamma-ray bursts travel across the universe at nearly the speed of light, and their light carries with it information about the fabric of space-time itself. One of the key predictions of Einstein's theory is that all forms of light, regardless of their wavelength, should travel at the same speed in a vacuum. This principle, known as the universality of the speed of light, can be tested using gamma-ray bursts. By analyzing the arrival times of different wavelengths of light from a single burst, scientists can check whether high-energy gamma rays and lower-energy X-rays or optical light arrive simultaneously. Any deviation could hint at new physics beyond Einstein's theory, potentially revealing insights into quantum gravity or other exotic phenomena. Another fascinating way gamma-ray bursts test relativity is through their interaction with gravitational fields. When the light from a gamma-ray burst passes near massive objects like galaxies or black holes, it can be bent or distorted by the warping of spacetime, an effect known as gravitational lensing. By studying these distortions, astronomers can measure the mass of the intervening objects and test the predictions of general relativity on cosmic scales. This not only confirms Einstein's theory, but also helps map the distribution of dark matter in the universe. Gamma-ray bursts also provide a unique opportunity to explore the concept of time dilation, another cornerstone of relativity. Because these bursts occur at such vast distances, their light takes billions of years to reach us. During this journey, the expansion of the universe stretches the light, causing it to appear slower and redder, a phenomenon known as cosmological redshift. By comparing the observed properties of gamma-ray bursts with their expected behavior, scientists can test how time and space behave over immense distances and timescales, further validating Einstein's framework. The implications of these tests are profound. If gamma-ray bursts were to reveal even the slightest deviation from Einstein's predictions, it could revolutionize our understanding of physics, opening the door to new theories that unify gravity with the other fundamental forces of nature. Even without such a breakthrough, the precision with which gamma-ray bursts confirm relativity deepens our confidence in the theory and sharpens our tools for exploring the universe. As we continue to study these cosmic explosions, we not only uncover the secrets of gamma-ray bursts but also push the boundaries of human knowledge, testing the very laws that govern reality. Next, we'll explore the most energetic gamma-ray burst ever recorded and what it taught us about the extremes of the universe. But for now, let's marvel at how these bursts serve as cosmic experiments, helping us probe the deepest mysteries of physics. Now, let's turn our attention to a gamma-ray burst that stands out even among these cosmic titans, GRB 130427a, the most energetic gamma-ray burst ever recorded. Detected in April 2013, this colossal explosion released an unprecedented amount of energy, shining brighter than 1,000,000 trillion suns for a brief moment. Its sheer power challenged our understanding of what gamma-ray bursts are capable of and provided a treasure trove of data for scientists to analyze. GRB 130427 was a long-duration burst lasting nearly 20 seconds, and it originated from a galaxy located about 3.6 billion light-years away. What made this burst truly remarkable was not just its distance or duration, but the incredible energy it unleashed. The initial gamma-ray flash was so intense that it saturated the detectors on NASA's Fermi Gamma-Ray Space Telescope, an instrument specifically designed to handle extreme cosmic events. This burst also produced an exceptionally bright afterglow, visible in X-ray, optical, and radio wavelengths, allowing astronomers to study it in unprecedented detail. One of the key revelations from GRB 130427 was the confirmation of a theoretical prediction about gamma-ray bursts. Scientists had long suspected that the jets produced by these explosions could carry energy in the form of magnetic fields known as Poynting flux. Observations of this burst provided strong evidence for this mechanism, showing how magnetic fields play a crucial role in shaping and powering the jets. This discovery deepened our understanding of the physics behind gamma-ray bursts and how they channel such immense energy into narrow beams of light. Another fascinating aspect of GRB 130427 was its connection to the collapse of a massive star. The burst's characteristics aligned with the model of a hypernova, a supernova on steroids, where the core of a massive star collapses into a black hole, releasing a tremendous amount of energy. This event not only confirmed the link between long-duration gamma-ray bursts and the deaths of massive stars, but also provided new insights into the conditions required for such extreme explosions to occur. The study of GRB 130427 also highlighted the importance of multi-wavelength observations. By combining data from gamma-ray, X-ray, optical, and radio telescopes, scientists were able to piece together a comprehensive picture of the burst's behavior, from its initial explosion to its fading afterglow. This collaborative approach has become a cornerstone of modern gamma-ray burst research, enabling us to uncover the secrets of these cosmic phenomena. As we reflect on GRB 130427a, it's clear that this burst was more than just a record-breaking event. It was a cosmic beacon that illuminated the extreme physics of the universe. Its discovery not only expanded our knowledge of gamma-ray bursts, but also reminded us of the incredible power and mystery that lie hidden in the depths of space. Next, we'll explore how gamma-ray bursts act as cosmic flashlights, shedding light on the early universe and its evolution. But for now, let's marvel at the sheer energy and brilliance of GRB 130427A, a true titan among cosmic explosions. Now, let's shift our focus to how gamma-ray bursts serve as cosmic flashlights, casting light on the mysteries of the early universe. These powerful explosions are not just fleeting moments of brilliance, they are also invaluable tools for astronomers, offering a glimpse into the universe's infancy and its dramatic evolution over billions of years. Gamma-ray bursts are so luminous that they can be detected from the farthest reaches of the cosmos, even from regions that existed when the universe was just a fraction of its current age. When a gamma-ray burst occurs, its intense light travels across vast distances, passing through clouds of gas, dust, and other cosmic structures. As this light interacts with these materials, it carries with it information about the conditions it encountered along the way. This makes gamma-ray bursts like cosmic messengers, delivering clues about the composition and structure of the early universe. One of the most remarkable aspects of gamma-ray bursts is their ability to reveal the presence of the first stars and galaxies. These bursts often originate from regions where massive stars are forming and dying, and their light can illuminate the environments around them. By studying the afterglows of gamma-ray bursts, astronomers can detect the faint signatures of ancient galaxies and even the first generation of stars, known as population 3 stars. These stars, which formed shortly after the Big Bang, are thought to have been incredibly massive and short-lived, and their existence has been difficult to confirm directly. Gamma-ray bursts provide a unique window into this elusive era of cosmic history. Another way gamma-ray bursts help us study the early universe is by acting as probes of the intergalactic medium, the diffuse gas that fills the space between galaxies. As the light from a gamma-ray burst travels through this medium, it gets absorbed at specific wavelengths, creating a kind of fingerprint that reveals the chemical composition and density of the gas. This information allows scientists to map the distribution of matter in the early universe and understand how it evolved over time. In essence, gamma-ray bursts are like cosmic X-rays, allowing us to peer into the universe's hidden structures. Gamma-ray bursts also play a crucial role in studying the epoch of reionization, a pivotal period in the universe's history when the first stars and galaxies began to ionize the surrounding hydrogen gas. This process transformed the universe from a dark, opaque state to the transparent cosmos we see today. By analyzing the light from gamma-ray bursts that occurred during this era, astronomers can piece together how and when reionization took place, shedding light on one of the most transformative phases in cosmic history. In addition to their scientific value, gamma-ray bursts also challenge our understanding of the universe's early conditions. For example, the detection of extremely distant bursts has pushed the limits of our observational capabilities, forcing us to refine our models of how stars and galaxies formed in the first billion years after the Big Bang. These bursts serve as both a test and a guide, helping us refine our theories about the universe's origins and evolution. As we continue to study gamma-ray bursts, it's clear that these cosmic explosions are more than just spectacular displays of energy. They are essential tools for exploring the universe's deepest mysteries. By acting as cosmic flashlights, they illuminate the distant past, revealing the conditions and processes that shape the cosmos as we know it. Next, we'll delve into the intriguing connection between gamma-ray bursts and dark matter, another enigmatic piece of the cosmic puzzle. But for now, let's appreciate how gamma-ray bursts light the way to understanding the universe's earliest moments. Now, let's turn our attention to one of the most intriguing mysteries in modern astrophysics, the potential connection between gamma-ray bursts and dark matter. While gamma-ray bursts are already fascinating in their own right, their possible link to dark matter adds another layer of cosmic intrigue. Dark matter, which makes up about 27% of the universe, is invisible and doesn't interact with light, making it incredibly difficult to detect directly. Yet, its gravitational effects are undeniable, shaping the structure of galaxies and the universe itself. So how could gamma-ray bursts, these brilliant flashes of energy, be connected to something so elusive? One theory suggests that gamma-ray bursts could be influenced by dark matter in ways we're only beginning to understand. For instance, some researchers propose that dark matter particles might accumulate in the cores of massive stars. When these stars collapse and trigger a gamma-ray burst, the interaction between the burst and the dark matter could produce unique signatures in the energy output. These signatures, if detected, might provide indirect evidence of dark matter's presence and properties. While this idea is still speculative, it opens up exciting possibilities for using gamma-ray bursts as tools to probe the nature of dark matter. Another intriguing hypothesis involves the role of dark matter in the formation of gamma-ray bursts themselves. Some models suggest that dark matter could play a part in the collapse of massive stars or the merging of neutron stars, both of which are known to produce gamma-ray bursts. If dark matter interacts with these processes, even in subtle ways, it could leave behind clues in the burst's afterglow or energy distribution. Scientists are actively studying these possibilities, analyzing data from gamma-ray bursts to search for any anomalies that might hint at dark matter's involvement. Ongoing research is also exploring whether gamma-ray bursts could help map the distribution of dark matter in the universe. Since dark matter doesn't emit light, its presence is typically inferred through its gravitational effects on visible matter. However, gamma-ray bursts, with their intense light traveling across vast distances, might offer another way to trace dark matter. As the light from a gamma-ray burst passes through regions rich in dark matter, it could be subtly altered in ways that reveal the dark matter's density and distribution. This approach is still in its early stages, but it holds promise for uncovering new insights into the cosmic web of dark matter. While the connection between gamma-ray bursts and dark matter remains speculative, the potential implications are profound. If gamma-ray bursts can indeed shed light on dark matter, they could help solve one of the biggest mysteries in astrophysics. This research not only deepens our understanding of gamma-ray bursts, but also brings us closer to unraveling the secrets of dark matter and its role in the universe. As we continue to explore this fascinating link, gamma-ray bursts may prove to be even more versatile tools for cosmic discovery than we ever imagined. Next, we'll dive into how gamma-ray bursts influence the evolution of galaxies, shaping the cosmos in ways that extend far beyond their explosive origins. Now, shifting our focus to the broader cosmic stage, let's explore how gamma-ray bursts play a surprising role in shaping the evolution of galaxies. These explosive events, often thought of as destructive, actually contribute to the birth of new stars and the spread of essential elements across the universe. When a gamma-ray burst occurs, it releases an enormous amount of energy, which can have a ripple effect on the surrounding space. This energy can compress nearby gas clouds, triggering the collapse of these clouds and igniting the formation of new stars. In this way, gamma-ray bursts act as cosmic catalysts, turning regions of dormant gas into stellar nurseries, but their influence doesn't stop there. Gamma-ray bursts are also responsible for dispersing heavy elements like gold and platinum into the cosmos. These elements are forged in the extreme conditions of the burst itself or in the supernova that often accompany long-duration gamma-ray bursts. As the explosion sends shockwaves through space, it scatters these heavy elements far and wide, enriching the interstellar medium. Over time, these elements become part of new stars, planets, and even life itself. Without gamma-ray bursts, the universe might lack the diversity of elements necessary for complex structures to form. Interestingly, the impact of gamma-ray bursts on galactic evolution isn't uniform. In smaller galaxies where star formation is already less frequent, a single gamma-ray burst can have a more pronounced effect. The burst's energy can heat up the surrounding gas, temporarily halting star formation. However, once the gas cools, it often leads to a burst of new star formation, creating a cycle of destruction and creation. In larger galaxies where star formation is more continuous, gamma-ray bursts contribute to the ongoing process of galactic enrichment, ensuring that heavy elements are distributed throughout the galaxy. Scientists are also studying how gamma-ray bursts might influence the structure of galaxies over long timescales. By analyzing the distribution of gamma-ray bursts and their aftereffects, researchers can gain insights into how galaxies grow and change. These bursts, though fleeting, leave behind a lasting legacy, shaping the chemical and structural evolution of galaxies in ways we're only beginning to understand. As we continue to study these cosmic explosions, we uncover more about their role in the grand tapestry of the universe. Next, we'll take a closer look at how gamma-ray bursts help us study the ancient universe, acting as cosmic flashlights that illuminate the distant past. Now, let's journey even further back in time to uncover how gamma-ray bursts serve as cosmic time capsules, allowing us to peer into the ancient universe. When astronomers detect gamma-ray bursts, they're not just observing a fleeting explosion, they're capturing light that has traveled across billions of light years. This light carries with it a snapshot of the universe as it existed when the burst first occurred, offering a rare glimpse into the conditions of the early cosmos. Studying these ancient bursts is no small feat. One of the biggest challenges is the sheer distance involved. The light from the most distant gamma-ray bursts has been traveling for over 13 billion years, meaning we're seeing these events as they happened when the universe was in its infancy. To detect such faint signals, astronomers rely on incredibly sensitive instruments, like the Hubble Space Telescope and ground-based observatories equipped with advanced spectrographs. These tools allow scientists to analyze the light in detail, revealing clues about the composition of the early universe and the environments in which these bursts occurred. One of the most fascinating discoveries from studying ancient gamma-ray bursts is the evidence they provide about the universe's reionization era. This was a period when the first stars and galaxies formed, flooding the cosmos with ultraviolet light that ionized the surrounding hydrogen gas. Gamma-ray bursts from this era act as beacons, illuminating the transition from a dark, neutral universe to one filled with light and structure. By analyzing the absorption lines in the light from these bursts, astronomers can map how the universe evolved during this critical phase. Another challenge lies in interpreting the data. The light from ancient gamma-ray bursts passes through countless galaxies and clouds of gas before reaching us, each leaving its own imprint. This makes it difficult to isolate the original signal from the burst itself. However, these obstacles also present opportunities. By studying how the light is altered as it travels, scientists can learn about the distribution of matter in the universe and the properties of the intergalactic medium. Despite these challenges, the rewards are immense. Ancient gamma-ray bursts have revealed that the early universe was far more dynamic and complex than previously thought. They've shown us that even in its infancy, the cosmos was capable of producing some of the most energetic events imaginable. As we continue to refine our techniques and build more powerful telescopes, we'll undoubtedly uncover even more secrets hidden in the light of these ancient explosions. Next, we'll explore how gamma-ray bursts contribute to the production of cosmic dust, a key ingredient in the formation of stars and planets. Now, let's shift our focus to the role gamma-ray bursts play in the cosmic chemistry of the universe. These explosive events are not just spectacular light shows, they're also cosmic forges, creating and scattering some of the heaviest elements in existence. Elements like gold, platinum, and uranium, which are essential to the formation of planets and even life itself, owe their origins in part to the extreme conditions generated by gamma-ray bursts. When a gamma-ray burst occurs, the immense energy released triggers a process called nucleosynthesis. This is where lighter elements like hydrogen and helium are fused together under extreme temperatures and pressures to form heavier elements. In the case of long-duration gamma-ray bursts, which are linked to the collapse of massive stars, the explosion is so powerful that it can produce elements far heavier than iron. These elements are then ejected into space at incredible speeds, seeding the surrounding regions with the building blocks of future stars, planets, and even life. But the story doesn't end there. The jets of material produced by gamma-ray bursts travel vast distances, carrying these heavy elements across galaxies. Over billions of years, these elements become incorporated into clouds of gas and dust, which eventually collapse to form new stars and planetary systems. This means that the gold in your jewelry or the platinum in a catalytic converter might have originated in a gamma-ray burst that occurred billions of years ago, long before our solar system even existed. What's truly remarkable is how gamma-ray bursts contribute to the diversity of elements in the universe. Without these cosmic explosions, many of the heavy elements we rely on today might never have formed. They've played a crucial role in enriching the cosmos, ensuring that the universe is filled with the chemical complexity needed to support life as we know it. As we continue to study gamma-ray bursts, we're uncovering more about their role in shaping the chemical landscape of the universe. These discoveries not only deepen our understanding of cosmic evolution, but also highlight the interconnectedness of all things in the cosmos. Next, we'll delve into the intriguing connection between gamma-ray bursts and supermassive black holes, exploring how these two phenomena are intertwined in the grand tapestry of the universe. Now, let's turn our attention to one of the most fascinating connections in the cosmos, the relationship between gamma-ray bursts and supermassive black holes. These two phenomena, though seemingly unrelated, are deeply intertwined in the grand dance of the universe. Supermassive black holes, which reside at the heart of nearly every galaxy, are known for their immense gravitational pull and their ability to influence their surroundings on a colossal scale. But how do they connect to gamma-ray bursts, the most energetic explosions in the universe? One of the key links lies in the environments where gamma-ray bursts occur. Many long-duration gamma-ray bursts are associated with the collapse of massive stars in regions of active star formation. These regions are often found near the centers of galaxies, where supermassive black holes exert their influence. The intense gravitational forces and high-energy processes around these black holes can create conditions that are ripe for the birth of massive stars. Stars that may eventually end their lives in spectacular gamma-ray bursts. But the connection goes even deeper. Some gamma-ray bursts are thought to be triggered by the interaction of stars with supermassive black holes. For instance, if a star gets too close to a black hole, it can be torn apart in a process called tidal disruption. This violent event can produce a jet of high-energy particles, which, under the right conditions, might be observed as a gamma-ray burst. While these events are rare, they provide a unique window into the extreme physics at play near supermassive black holes. Another intriguing possibility is that supermassive black holes themselves could be the engines behind certain types of gamma-ray bursts. In active galactic nuclei, where supermassive black holes are feeding on surrounding matter, the accretion process can generate powerful jets of particles traveling at nearly the speed of light. These jets, when pointed directly at Earth, can produce gamma-ray emissions that resemble those of traditional gamma-ray bursts. This suggests that supermassive black holes might be capable of producing their own versions of these cosmic explosions. Understanding the connection between gamma-ray bursts and supermassive black holes not only sheds light on the behavior of these enigmatic objects, but also helps us piece together the broader story of galactic evolution. By studying these interactions, astronomers can gain insights into how black holes shape their host galaxies and influence the formation of stars and planetary systems. As we continue to explore this cosmic relationship, we uncover more about the intricate web of forces that govern the universe. Next, we'll dive into how gamma-ray bursts help us probe the intergalactic medium, the vast and mysterious space between galaxies. Now, let's shift our focus to the vast and mysterious space between galaxies, known as the intergalactic medium. This diffuse gas, though invisible to the naked eye, plays a crucial role in the structure and evolution of the universe. Gamma-ray bursts, with their incredible brightness and far-reaching light, serve as powerful tools for probing this elusive cosmic environment. When a gamma-ray burst occurs, its intense light travels across the universe, passing through the intergalactic medium on its way to Earth. As this light interacts with the gas and dust in the intergalactic medium, it leaves behind subtle fingerprints in the form of absorption lines. These lines, detected by telescopes, reveal the composition, density, and temperature of the gas that the light has traveled through. In essence, gamma-ray bursts act like cosmic flashlights, illuminating the otherwise invisible material that fills the space between galaxies. One of the most fascinating aspects of this process is how it allows astronomers to map the distribution of matter in the universe. By studying the absorption lines from multiple gamma-ray bursts, scientists can piece together a three-dimensional picture of the intergalactic medium. This helps us understand how matter is distributed on the largest scales, from the filaments of the cosmic web to the vast voids that separate galaxy clusters. Gamma-ray bursts also provide insights into the history of the intergalactic medium. Over billions of years, the gas between galaxies has been shaped by processes like star formation, supernova explosions, and the activity of supermassive black holes. By analyzing the light from gamma-ray bursts at different distances and therefore different points in cosmic history, astronomers can trace how the intergalactic medium has evolved over time. This gives us a unique window into the dynamic processes that have shaped the universe since its earliest days. Moreover, gamma-ray bursts help us study the chemical makeup of the intergalactic medium. The absorption lines in their light reveal the presence of elements like hydrogen, helium, and even heavier elements forged in the hearts of stars. This information is crucial for understanding how the universe has been enriched with these elements over time, a process that has ultimately made life as we know it possible. In summary, gamma-ray bursts are not just spectacular cosmic explosions, they are also invaluable tools for exploring the hidden realms of the intergalactic medium. By shedding light on this diffuse gas, they help us uncover the secrets of the universe's structure, history, and evolution. Next, we'll explore the ongoing mystery of what causes gamma-ray bursts, diving into the debate about their progenitors and the theories that attempt to explain their origins. Now, let's turn our attention to one of the most intriguing mysteries surrounding gamma-ray bursts: what exactly causes them. Despite decades of research, the question of what creates these powerful cosmic explosions remains a topic of intense debate among scientists. The search for the progenitors, or the objects responsible for gamma-ray bursts, has led to a variety of theories, each supported by compelling evidence but still leaving room for further discovery. One of the leading theories points to the collision of neutron stars as the source of short-duration gamma-ray bursts. Neutron stars are the incredibly dense remnants of massive stars that have exploded in supernova. When two neutron stars spiral toward each other and eventually merge, the resulting collision releases an enormous amount of energy in the form of gravitational waves and a gamma-ray burst. This theory gained significant support in 2017, when the detection of gravitational waves from a neutron-star merger coincided with a short gamma-ray burst, providing strong evidence for this connection. On the other hand, long-duration gamma-ray bursts are thought to originate from the collapse of massive stars, often referred to as hypernova. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses under its own gravity, forming a black hole. As this happens, jets of material are launched outward at nearly the speed of light, producing a gamma-ray burst that can last for several seconds or even minutes. Observations of supernova occurring in the same regions as long gamma-ray bursts have bolstered this theory, linking these cosmic explosions to the death throes of massive stars. However, not all gamma-ray bursts fit neatly into these categories. Some events, known as ultra-long gamma-ray bursts, last for hours instead of seconds or minutes, challenging our understanding of their origins. One possibility is that these ultra-long bursts are caused by the collapse of extremely massive stars, far larger than those responsible for typical long bursts. Another theory suggests they may result from the tidal disruption of stars by supermassive black holes, though this remains an area of active research. Adding to the complexity, some gamma-ray bursts appear to lack the typical afterglow or host galaxy, making it difficult to trace their origins. These so-called orphan bursts raise questions about whether they come from entirely different progenitors or if they are simply the result of unusual conditions in their environments. The mystery of gamma-ray burst progenitors is far from solved, but each new discovery brings us closer to understanding these extraordinary events. As astronomers continue to study gamma-ray bursts with increasingly advanced tools, they hope to unravel the secrets of their origins and uncover the cosmic processes that give rise to the universe's most powerful explosions. Next, we'll explore how gamma-ray bursts may have played a role in one of the most transformative periods in the universe's history, the era of cosmic reionization. Now, let's shift our focus to a pivotal moment in the universe's history, cosmic reionization, and explore how gamma-ray bursts may have played a crucial role in this transformative era. Cosmic reionization refers to the period when the universe transitioned from being a dark, neutral state to one filled with ionized gas, allowing light to travel freely through space. This process began roughly 400 million years after the Big Bang and lasted for several hundred million years, fundamentally shaping the universe as we know it today. During the early universe, the first stars and galaxies began to form, emitting intense ultraviolet light. This light had the power to strip electrons from hydrogen atoms, ionizing the gas that filled the cosmos. However, the exact mechanisms behind this process remain a topic of active research. This is where gamma-ray bursts come into the picture. Scientists theorize that these incredibly energetic explosions may have contributed significantly to reionization by emitting vast amounts of high-energy radiation, capable of ionizing hydrogen atoms across vast distances. Gamma-ray bursts, particularly those occurring in the early universe, would have released not only gamma rays but also ultraviolet and X-ray radiation. These emissions could have penetrated dense regions of neutral hydrogen, ionizing the gas and helping to clear the cosmic fog. In this way, gamma-ray bursts may have acted as cosmic flashlights, illuminating the universe and accelerating the process of reionization. Their role would have been especially important in regions where the light from early stars and galaxies was too weak to fully ionize the surrounding gas. Moreover, the afterglows of gamma-ray bursts could have provided additional ionizing radiation, further contributing to the reionization process. As these afterglows faded, they would have left behind pockets of ionized gas, creating pathways for light to travel through the universe. This would have allowed the first galaxies to become visible and set the stage for the large-scale structure of the cosmos to emerge. The study of gamma-ray bursts from the early universe offers a unique window into this critical period. By analyzing the light from these distant explosions, astronomers can gather clues about the conditions of the universe during reionization. For instance, the absorption features in the spectra of gamma-ray burst afterglows can reveal the density and ionization state of the gas they pass through, providing valuable insights into how reionization unfolded. While the exact contribution of gamma-ray bursts to cosmic reionization is still being investigated, their potential impact is undeniable. These cosmic explosions may have been among the key players in transforming the universe from a dark, neutral state into the vibrant, ionized cosmos we observe today. As we continue to uncover more about gamma-ray bursts and their role in the early universe, we gain a deeper understanding of the forces that shape the cosmos. Next, we'll delve into another fascinating connection: how gamma-ray bursts relate to fast radio bursts, another mysterious phenomenon in the universe. Now, let's turn our attention to another cosmic mystery that shares some intriguing parallels with gamma-ray bursts, fast radio bursts. These fleeting but powerful signals have puzzled astronomers since their discovery, and their connection to gamma-ray bursts offers a fascinating area of exploration. Fast radio bursts, or FRB, are brief, intense flashes of radio waves that last only milliseconds, yet they release as much energy as the sun does in an entire day. Like gamma-ray bursts, they originate from distant corners of the universe, but their exact causes remain shrouded in mystery. One of the key similarities between gamma-ray bursts and fast radio bursts lies in their immense energy output. Both phenomena are among the most energetic events in the cosmos, capable of releasing staggering amounts of energy in a fraction of a second. However, while gamma-ray bursts are detected in the high-energy gamma-ray spectrum, fast radio bursts are observed in the radio wavelength, making them distinct in how they are studied and detected. This difference in wavelength also suggests that the mechanisms behind these two phenomena may not be identical, even if they share some common origins. Another point of connection is the potential role of neutron stars. Just as neutron star mergers are thought to produce short gamma-ray bursts, some fast radio bursts are believed to originate from highly magnetized neutron stars known as magnetars. These exotic objects, with their incredibly strong magnetic fields, could generate the intense bursts of radio waves observed in FRBs. In fact, some gamma-ray bursts and fast radio bursts have been detected in close proximity, leading scientists to speculate that they might be linked by the same astrophysical processes. Despite these similarities, there are also notable differences. Gamma-ray bursts are typically longer in duration, ranging from milliseconds to several minutes, while fast radio bursts are almost always confined to milliseconds. Additionally, gamma-ray bursts are often accompanied by afterglows in X-ray, optical, and radio wavelengths, whereas fast radio bursts are usually isolated events without detectable afterglows. This distinction makes fast radio bursts even more challenging to study, as they leave fewer clues for astronomers to analyze. The study of both gamma-ray bursts and fast radio bursts has opened new windows into the universe's most extreme environments. By comparing these two phenomena, scientists hope to uncover the underlying physics that drives such powerful cosmic events. For instance, understanding the relationship between gamma-ray bursts and fast radio bursts could shed light on the behavior of neutron stars, the nature of magnetic fields in extreme conditions, and even the distribution of matter in the universe. As research continues, the connection between gamma-ray bursts and fast radio bursts remains an exciting frontier in astrophysics. Each discovery brings us closer to unraveling the mysteries of these cosmic explosions and their role in shaping the universe. Next, we'll explore how gamma-ray bursts provide unique insights into the magnetic fields that permeate the cosmos, offering another piece of the puzzle in our quest to understand the universe's most distant and energetic events. Now, let's shift our focus to another fascinating aspect of gamma-ray bursts: their ability to help us study the magnetic fields that stretch across the cosmos. These invisible forces play a crucial role in shaping the universe, and gamma-ray bursts offer a unique window into understanding their behavior and influence. Gamma-ray bursts are not just powerful explosions, they are also cosmic laboratories for studying magnetic fields. When a gamma-ray burst occurs, it sends out jets of particles and radiation that travel through space at nearly the speed of light. These jets interact with the magnetic fields they encounter, and by observing how the light from the burst is affected, scientists can map the strength and structure of these fields. This process is similar to shining a flashlight through a fog. The way the light scatters reveals details about the environment it passes through. One of the key challenges in studying cosmic magnetic fields is their complexity. These fields are not uniform, they vary in strength and direction across different regions of space. Gamma-ray bursts, with their intense energy and wide-reaching jets, provide a way to probe these variations. For example, the polarization of light from a gamma-ray burst's afterglow can reveal information about the magnetic fields in the surrounding area. Polarization refers to the orientation of light waves, and when light passes through a magnetic field, its polarization changes in predictable ways. By analyzing these changes, astronomers can piece together a picture of the magnetic environment. Another breakthrough in this field has come from combining observations of gamma-ray bursts with other types of data, such as gravitational waves. When a gamma-ray burst is detected alongside a gravitational wave signal, it often points to a neutron-star merger as the source. These events are thought to produce some of the strongest magnetic fields in the universe. By studying the gamma-ray bursts associated with these mergers, scientists can learn more about how magnetic fields are generated and how they evolve in extreme conditions. Despite these advances, there are still many unanswered questions. For instance, how do magnetic fields influence the formation of galaxies and the distribution of matter in the universe? And what role do they play in the acceleration of cosmic rays, high-energy particles that travel through space at incredible speeds? Gamma-ray bursts continue to be a valuable tool in addressing these questions, offering insights that would be difficult to obtain through other means. As we continue to study gamma-ray bursts and their interactions with magnetic fields, we gain a deeper understanding of the forces that shape our universe. These cosmic explosions not only illuminate the darkest corners of space, but also help us unravel the mysteries of the invisible forces that govern it. Next, we'll explore how gamma-ray bursts could impact exoplanets and the potential implications for life beyond our solar system. Now, let's turn our attention to a thought-provoking question. What happens when a gamma-ray burst occurs near an exoplanet? These powerful cosmic explosions don't just light up the universe, they can also have profound effects on planets orbiting distant stars, potentially reshaping their atmospheres and even influencing the possibility of life. Gamma-ray bursts release an immense amount of energy in a very short time, and if one were to occur close to an exoplanet, the consequences could be dramatic. The intense radiation from a gamma-ray burst can strip away a planet's atmosphere, particularly if the planet lacks a strong magnetic field to protect it. This process, known as atmospheric erosion, could leave a once habitable world barren and lifeless. Imagine a planet with oceans and a thick atmosphere suddenly losing its protective layers, exposing its surface to harmful radiation from its star and the broader universe. But the effects don't stop there. Gamma-ray bursts also produce high-energy particles that can penetrate a planet's atmosphere and reach its surface. These particles can damage DNA and other biological molecules, posing a significant threat to any life forms that might exist. For planets in the path of a gamma-ray burst, the sudden influx of radiation could trigger mass extinctions, similar to what some scientists believe happened on Earth during past cosmic events. Interestingly, gamma-ray bursts might also play a role in shaping the conditions for life in unexpected ways. Some researchers suggest that the intense radiation from these bursts could trigger chemical reactions in a planet's atmosphere, potentially leading to the formation of complex molecules necessary for life. While this is still a topic of debate, it highlights the dual nature of gamma-ray bursts. They can be both destructive and, in some cases, creative forces in the universe. The likelihood of a gamma-ray burst affecting an exoplanet depends on several factors, including the distance between the burst and the planet's atmosphere, and its magnetic field. Planets in star-forming regions where gamma-ray bursts are more common are at greater risk. However, even in quieter parts of the galaxy, the possibility of a nearby gamma-ray burst cannot be ruled out entirely. As we continue to discover more exoplanets, understanding the impact of gamma-ray bursts becomes increasingly important. These cosmic events remind us that the universe is a dynamic and sometimes dangerous place, where the fate of entire worlds can hinge on the timing and location of a single explosion. Next, we'll delve into how gamma-ray bursts serve as cosmic time capsules, helping us peer into the ancient universe and uncover its secrets. Now, let's shift our focus to how gamma-ray bursts serve as cosmic time capsules, offering us a rare glimpse into the ancient universe. These powerful explosions act like flashlights, illuminating the distant past and allowing astronomers to study conditions that existed billions of years ago. By analyzing the light from gamma-ray bursts, scientists can piece together the history of the cosmos, uncovering details about the early universe that would otherwise remain hidden. When a gamma-ray burst occurs, its light travels across vast distances, passing through galaxies, gas clouds, and other cosmic structures along the way. As this light interacts with these materials, it carries with it information about the composition, density, and temperature of the universe at different points in time. This makes gamma-ray bursts invaluable tools for cosmic archaeology, helping researchers reconstruct the timeline of the universe's evolution. One of the most fascinating aspects of gamma-ray bursts is their ability to reveal the chemical makeup of the early universe. By studying the absorption lines in the light from these bursts, astronomers can identify the presence of elements like hydrogen, helium, and even heavier metals. This provides clues about how and when these elements were formed, shedding light on the processes that shaped the cosmos in its infancy. Gamma-ray bursts also help scientists study the reionization era, a pivotal period in the universe's history when the first stars and galaxies formed. The intense radiation from these early stars ionized the surrounding gas, transforming the universe from a dark, opaque state to the transparent one we see today. Gamma-ray bursts from this era act as probes, allowing astronomers to measure the properties of the intergalactic medium and understand how reionization unfolded. In addition to their role in studying the early universe, gamma-ray bursts also provide insights into the formation of galaxies and the distribution of matter on large scales. By mapping the locations of these bursts, astronomers can trace the cosmic web, the vast network of filaments and voids that make up the universe's structure. This helps us understand how galaxies and galaxy clusters formed and evolved over time. As we continue to detect and study more gamma-ray bursts, our understanding of the ancient universe grows deeper. These cosmic explosions are not just fleeting moments of brilliance, they are windows into the past, offering us a chance to explore the origins of everything we see today. Next, we'll explore the intriguing connection between gamma-ray bursts and high-energy neutrino emissions, and what this means for our understanding of particle physics. Now, let's turn our attention to an intriguing connection that bridges the worlds of gamma-ray bursts and particle physics. The potential link between these cosmic explosions and high-energy neutrino emissions. Neutrinos, often called ghost particles, are nearly massless subatomic particles that rarely interact with matter, making them incredibly difficult to detect. Yet, when they do interact, they can provide invaluable insights into some of the most extreme environments in the universe. Gamma-ray bursts, with their immense energy and violent origins, are thought to be natural accelerators capable of producing not just gamma rays but also high-energy neutrinos. Scientists hypothesize that during the formation of a gamma-ray burst, particularly in the chaotic aftermath of a neutron star merger or a supernova, particles are accelerated to near light speeds. These accelerated particles can collide with surrounding matter or radiation, producing neutrinos with energies far beyond what we can create in particle accelerators on Earth. The detection of neutrinos associated with gamma-ray bursts would be a groundbreaking discovery. It would not only confirm the connection between these two phenomena, but also provide a new way to study the physics of extreme environments. Neutrinos, unlike gamma rays, can travel vast distances without being absorbed or scattered, offering a direct line of sight to the heart of these cosmic explosions. This makes them ideal messengers for probing the inner workings of gamma-ray bursts, where conditions are too extreme for even light to escape unscathed. One of the most exciting implications of this connection lies in the field of multi-messenger astronomy. By combining observations of gamma-ray bursts with neutrino detections, scientists can gain a more complete picture of these events. For example, if a neutrino detector like Ice Cube in Antarctica picks up a high-energy neutrino at the same time a gamma-ray burst is observed, it could provide crucial evidence about the mechanisms powering these bursts. This synergy between different types of observations could revolutionize our understanding of particle acceleration, magnetic fields, and the behavior of matter under extreme conditions. Moreover, the study of gamma-ray bursts and neutrinos could shed light on some of the biggest questions in particle physics, such as the nature of dark matter and the properties of neutrinos themselves. High-energy neutrinos produced in gamma-ray bursts might carry signatures of interactions with dark matter or reveal new physics beyond the standard model. This makes gamma-ray bursts not just cosmic flashlights, but also potential laboratories for exploring the fundamental laws of the universe. As we continue to refine our detection methods and expand our understanding of these phenomena, the connection between gamma-ray bursts and neutrinos promises to unlock new frontiers in both astrophysics and particle physics. Next, we'll delve into how gamma-ray bursts are helping scientists test theories of quantum gravity, pushing the boundaries of our knowledge even further. Now, let's explore how gamma-ray bursts are opening new doors in the quest to understand one of the most elusive theories in physics: quantum gravity. Quantum gravity aims to bridge the gap between two of the most successful yet seemingly incompatible frameworks in science: quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes the force of gravity on cosmic scales. Gamma-ray bursts, with their extreme energies and rapid emissions, offer a rare natural laboratory to test these theories. One of the key challenges in studying quantum gravity is that its effects are expected to be incredibly subtle, manifesting only at the smallest scales or under the most extreme conditions. Gamma-ray bursts, however, produce such intense energy and rapid changes that they might reveal tiny deviations from the predictions of classical physics. For instance, some theories of quantum gravity suggest that the fabric of spacetime itself might have a granular structure at the smallest levels, like a cosmic pixelation. This could cause high-energy gamma rays to travel at slightly different speeds depending on their energy, a phenomenon known as Lorentz invariance violation. Gamma-ray bursts, with their wide range of photon energies, are ideal for detecting such minute differences. Another intriguing possibility is that gamma-ray bursts could help us understand how gravity behaves in the presence of extreme magnetic fields or near the event horizons of black holes, where quantum effects are thought to dominate. The jets produced by gamma-ray bursts are some of the most magnetized and energetic environments in the universe, making them perfect testing grounds for theories that attempt to unify gravity with the other fundamental forces. By analyzing the light and particles emitted during these bursts, scientists can look for signatures of quantum gravity that might otherwise be impossible to observe. However, testing these theories is no small feat. The effects of quantum gravity are so tiny that even the most sensitive instruments struggle to detect them. Additionally, the vast distances gamma-ray bursts travel mean that their signals can be distorted by intervening matter or cosmic expansion, complicating the analysis. Despite these challenges, the potential breakthroughs are immense. Confirming even a small deviation from classical physics could revolutionize our understanding of the universe, offering clues about the nature of spacetime, the origin of the cosmos, and the fundamental laws that govern reality. As we continue to refine our observations and develop more advanced detectors, gamma-ray bursts remain at the forefront of this exciting frontier. They not only illuminate the distant reaches of the universe, but also shine a light on the deepest mysteries of physics itself. Next, we'll dive into the fascinating variability of gamma-ray bursts and what it tells us about their origins and behavior. Now, shifting our focus to the intriguing variability of gamma-ray bursts, we uncover one of the most puzzling aspects of these cosmic explosions. Unlike other astronomical events, gamma-ray bursts exhibit a wide range of emission patterns, from smooth and steady to wildly erratic. This variability has left scientists scratching their heads as it challenges our understanding of how these bursts are produced and what drives their behavior. One leading theory suggests that the variability is linked to the chaotic environment within the jets of gamma-ray bursts. These jets, which are launched at nearly the speed of light, are thought to be powered by the collapse of massive stars or the merger of neutron stars. As material is funneled into these jets, it encounters turbulent magnetic fields and shock waves, which can cause fluctuations in the energy output. This turbulence might explain why some bursts appear smooth while others flicker unpredictably. Another possibility is that the variability arises from the interaction between the jet and the surrounding material. As the jet plows through the star or the debris left behind by a merger, it can encounter dense clumps of gas or dust. These interactions can create sudden spikes or dips in the emission, leading to the erratic patterns we observe. Additionally, the rotation of the central engine, whether a black hole or a neutron star, could also play a role, as changes in the orientation of the jet might cause variations in the observed light. Observations have further complicated the picture. Some gamma-ray bursts show multiple peaks in their light curves, suggesting that the central engine might be active for longer than previously thought, restarting or pulsing in bursts. Others exhibit rapid flickering on timescales of milliseconds, hinting at processes occurring incredibly close to the central engine, where gravity and magnetic fields are at their most extreme. Despite these theories, the exact mechanisms behind gamma-ray burst variability remain elusive. Each new observation seems to add another layer of complexity, challenging existing models and pushing scientists to refine their understanding. What's clear, however, is that this variability holds crucial clues about the physics of these extreme events, from the behavior of matter under intense gravity to the dynamics of relativistic jets. As we continue to study these bursts with ever more sensitive instruments, we inch closer to unraveling the mystery of their variability. Each flicker and fluctuation in their light offers a glimpse into the chaotic and energetic processes that shape the most powerful explosions in the universe. Next, we'll explore how gamma-ray bursts contribute to cosmic feedback, influencing the evolution of galaxies and the universe itself. Now, let's turn our attention to the fascinating role gamma-ray bursts play in cosmic feedback, a process that shapes the evolution of galaxies and the universe itself. Cosmic feedback refers to the way energy and matter are redistributed throughout the cosmos, influencing how stars form and galaxies grow. Gamma-ray bursts, with their immense energy output, are key players in this cosmic balancing act. When a gamma-ray burst occurs, it releases an enormous amount of energy into its surroundings. This energy can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. In this way, gamma-ray bursts act as a kind of cosmic regulator, putting the brakes on star formation in their host galaxies. This process is particularly important in the early universe, where intense bursts of energy from gamma-ray bursts may have helped shape the first galaxies. But gamma-ray bursts don't just suppress star formation, they also contribute to it in unexpected ways. The shock waves and radiation from these explosions can compress nearby gas clouds, triggering the birth of new stars. This dual role, both inhibiting and promoting star formation, makes gamma-ray bursts a crucial factor in the complex dance of cosmic evolution. Additionally, gamma-ray bursts play a role in enriching the universe with heavy elements. The explosions that produce these bursts create and disperse elements like gold, platinum, and uranium into space. These elements eventually become part of new stars, planets, and even life itself. Without gamma-ray bursts, the universe might lack many of the building blocks necessary for the diversity of structures we see today. the influence of gamma-ray bursts extends beyond their immediate surroundings. The energy they release can travel vast distances, affecting the intergalactic medium, the diffuse gas that fills the space between galaxies. By heating this gas, gamma-ray bursts help regulate the flow of matter and energy on a cosmic scale, influencing the growth and evolution of entire galaxy clusters. Understanding the role of gamma-ray bursts in cosmic feedback is essential for piecing together the story of how the universe evolved from its early, chaotic state to the structured cosmos we observe today. These bursts are not just spectacular explosions, they are powerful forces that shape the very fabric of the universe. Next, we'll explore the connection between gamma-ray bursts and cosmic rays, another mysterious phenomenon that holds clues to the universe's most energetic processes. Now, let's shift our focus to another intriguing aspect of gamma-ray bursts: their potential connection to cosmic rays, those mysterious high-energy particles that constantly bombard our planet. Cosmic rays are some of the most energetic particles in the universe, traveling at nearly the speed of light. But where do they come from? Scientists have long suspected that gamma-ray bursts might be one of their sources, and the evidence is compelling. When a gamma-ray burst occurs, it doesn't just release gamma rays, it also produces a cascade of other particles, including protons and atomic nuclei. These particles can be accelerated to incredible speeds, becoming what we know as cosmic rays. The immense energy of gamma-ray bursts makes them prime candidates for generating these high-energy particles. In fact, some of the most energetic cosmic rays ever detected could have originated from these cosmic explosions. One of the key pieces of evidence linking gamma-ray bursts to cosmic rays comes from observations of their afterglows. As the burst's energy interacts with surrounding gas and dust, it creates shock waves that accelerate particles to extreme velocities. These accelerated particles can then escape into space, becoming cosmic rays that travel across the universe. This process is similar to how particles are accelerated in supernova remnants, but gamma-ray bursts pack an even more powerful punch. Theories also suggest that gamma-ray bursts could be responsible for producing ultra-high-energy cosmic rays, which are the most energetic particles ever observed. These particles carry so much energy that their origins have puzzled scientists for decades. Gamma-ray bursts, with their extreme energy output, are one of the few phenomena capable of producing such particles. If confirmed, this link would provide a major breakthrough in our understanding of both gamma-ray bursts and cosmic rays, but the connection doesn't stop there. Gamma-ray bursts may also help explain why cosmic rays are so diverse in their composition. The explosions that produce gamma-ray bursts can create and accelerate a wide range of particles, from protons to heavier atomic nuclei. This diversity could account for the variety of cosmic rays detected on Earth, offering a unified explanation for their origins. Understanding the relationship between gamma-ray bursts and cosmic rays is not just an academic exercise, it has real implications for our understanding of the universe. Cosmic rays play a role in shaping the interstellar medium, influencing star formation, and even affecting the chemistry of planetary atmospheres. By studying their connection to gamma-ray bursts, we gain deeper insights into the forces that shape the cosmos. As we continue to explore this fascinating link, new discoveries are sure to emerge, shedding light on the origins of these high-energy particles and the role gamma-ray bursts play in their creation. Next, we'll dive into how gamma-ray bursts help astronomers map the cosmic web, the intricate structure that connects galaxies across the universe. Now, let's turn our attention to another remarkable way gamma-ray bursts contribute to our understanding of the universe by helping astronomers map the cosmic web. The cosmic web is the vast, intricate network of galaxies, gas, and dark matter that forms the backbone of the universe's large-scale structure. It's like a giant spider web with galaxies clustered along its filaments and vast voids in between. But how do gamma-ray bursts help us see this invisible framework? When a gamma-ray burst occurs, its intense light travels across the universe, passing through the cosmic web on its way to Earth. As this light interacts with the gas and matter in the web, it leaves behind subtle clues about the structure it has traveled through. By analyzing the light from gamma-ray bursts, astronomers can detect these clues, effectively using the bursts as cosmic flashlights to illuminate the web's hidden features. One of the key tools in this process is the study of absorption lines in the light from gamma-ray bursts. As the light passes through clouds of gas in the cosmic web, certain wavelengths are absorbed, creating distinct patterns in the burst spectrum. These patterns reveal the composition, density, and distribution of the gas, allowing scientists to piece together a map of the cosmic web. It's like using a flashlight to see the dust in a dark room. The light reveals what's otherwise invisible. Gamma-ray bursts are particularly useful for this purpose because they are so bright and can be observed from incredibly far away. This means they can illuminate parts of the cosmic web that are otherwise too distant or faint to study. By combining observations of multiple gamma-ray bursts, astronomers can build a more complete picture of the web's structure, tracing its filaments and voids across billions of light years. This mapping isn't just about creating a pretty picture, it's about understanding how the universe evolved. The cosmic web is a relic of the early universe, shaped by the forces of gravity and dark energy. By studying its structure, scientists can learn more about how galaxies formed, how matter is distributed, and even how the universe has expanded over time. Gamma-ray bursts, with their ability to probe the distant and ancient universe, are invaluable tools in this quest. As we continue to detect and study more gamma-ray bursts, our map of the cosmic web will become even more detailed, revealing new insights into the universe's architecture. Next, we'll explore the mystery of gamma-ray burst afterglow polarization and what it tells us about the physics of these incredible explosions. Now, let's dive into one of the most intriguing aspects of gamma-ray bursts, their afterglow polarization. When a gamma-ray burst occurs, the initial flash of gamma rays is often followed by a lingering afterglow, visible in X-rays, optical light, and radio waves. But what makes this afterglow even more fascinating is its polarization, a property of light that reveals the orientation of its waves as they travel through space. Polarization in gamma-ray burst afterglows occurs because the light emitted during the burst is not uniform. Instead, it's often aligned in specific directions, influenced by the magnetic fields and the structure of the jets that produce the burst. By studying this polarization, scientists can uncover critical details about the environment surrounding the burst, such as the strength and orientation of magnetic fields, the geometry of the jets, and even the mechanisms that power these colossal explosions. One of the key discoveries from studying polarized afterglows is that they provide evidence for the presence of strong magnetic fields in the jets of gamma-ray bursts. These fields play a crucial role in shaping the jets and accelerating particles to nearly the speed of light. Without polarization measurements, much of this information would remain hidden, as traditional observations of brightness and color alone can't reveal these subtle details. Another important insight from polarization is that it helps scientists understand the structure of gamma-ray burst jets. Some bursts produce highly polarized afterglows, suggesting their jets are narrow and tightly focused. Others show less polarization, indicating broader or more chaotic jets. This variation helps astronomers piece together the diversity of gamma-ray bursts and the different conditions under which they form. But why does this matter? Polarization isn't just a scientific curiosity, it's a powerful tool for testing our theories about how gamma-ray bursts work. For example, it allows researchers to verify whether the jets are powered by the collapse of massive stars or the merger of neutron stars. It also provides clues about how energy is transferred from the burst to its surroundings, shedding light on the physics of some of the most energetic events in the universe. As we continue to study polarized afterglows, we're not just solving the mystery of gamma-ray bursts. we're also gaining a deeper understanding of the fundamental forces and processes that shape the cosmos. Next, we'll explore how gamma-ray bursts help us probe the magnetic fields of the early universe, unlocking even more secrets about its origins and evolution. Now, let's shift our focus to one of the most profound mysteries of the cosmos: dark energy, and how gamma-ray bursts are helping us unravel its secrets. Dark energy, the enigmatic force driving the accelerated expansion of the universe, remains one of the biggest puzzles in modern astrophysics. While its existence was first inferred from observations of distant supernova, gamma-ray bursts are now emerging as powerful tools to probe this elusive phenomenon. Gamma-ray bursts, especially those at extreme distances, act as cosmic beacons that allow scientists to measure the expansion rate of the universe over vast stretches of time. By analyzing the light from these bursts, astronomers can determine how far away they are and how fast the universe was expanding when the light was emitted. This information is crucial for understanding how dark energy has influenced the universe's growth over billions of years. One of the key advantages of using gamma-ray bursts to study dark energy is their incredible brightness. Unlike supernova, which fade relatively quickly, gamma-ray bursts can be detected across much greater distances, providing a deeper look into the universe's past. This makes them ideal for mapping the large-scale structure of the cosmos and tracking changes in its expansion rate over time. Another important aspect is the role of gamma-ray bursts in testing alternative theories of gravity and dark energy. Some models suggest that dark energy might not be a constant force but could vary over time or interact with matter in unexpected ways. By comparing the distances and redshifts of gamma-ray bursts with other cosmic measurements, scientists can test these theories and refine our understanding of the universe's evolution. Interestingly, gamma-ray bursts also help astronomers study the distribution of dark energy across the universe. Because these bursts occur randomly and are distributed throughout space, they provide a unique way to measure the density of dark energy in different regions. This information can reveal whether dark energy is uniform or clumpy, offering clues about its nature and origin. As we continue to study gamma-ray bursts in the context of dark energy, we're not just exploring the universe's expansion, we're also challenging our fundamental understanding of physics. These cosmic explosions are helping us answer some of the most profound questions in science, from the nature of dark energy to the ultimate fate of the universe. Next, we'll delve into the fascinating connection between gamma-ray bursts and gravitational waves, and how these two phenomena are revolutionizing our view of the cosmos. Now, let's turn our attention to an exciting frontier in astrophysics: the connection between gamma-ray bursts and gravitational waves. These two phenomena, though seemingly unrelated, are now revealing a deeper cosmic relationship that is transforming our understanding of the universe. Gravitational waves, ripples in spacetime caused by massive cosmic events like neutron star collisions, were first detected in 2015, opening a new window into the cosmos. Remarkably, gamma-ray bursts are often linked to these same cataclysmic events, creating a unique opportunity for scientists to study the universe in a whole new way. When two neutron stars collide, they produce both gravitational waves and a gamma-ray burst. This dual emission allows astronomers to observe the same event through two completely different channels, one detecting ripples in spacetime and the other capturing high-energy light. This combination, known as multi-messenger astronomy, provides a richer, more detailed picture of these explosive events. For example, the historic detection of gravitational waves from a neutron star merger in 2017 was accompanied by a gamma-ray burst, marking the first time both signals were observed together. This groundbreaking discovery confirmed long-standing theories about the origins of short gamma-ray bursts and demonstrated the power of combining different types of cosmic observations. The implications of this connection are profound. By studying gamma-ray bursts and gravitational waves together, scientists can gain insights into the behavior of matter under extreme conditions, such as the density inside neutron stars. They can also measure the expansion rate of the universe with greater precision, as both signals provide independent ways to calculate distances. Additionally, these observations help test Einstein's theory of general relativity in new and extreme environments, offering clues about the fundamental laws of physics. One of the most exciting aspects of this research is its potential to uncover the origins of heavy elements like gold and platinum. Neutron star collisions are thought to be cosmic factories for these elements, and the combined study of gamma-ray bursts and gravitational waves provides direct evidence of this process. By analyzing the light and ripples from these events, scientists can trace the creation and distribution of these precious materials across the universe. As we continue to explore the link between gamma-ray bursts and gravitational waves, we're not just witnessing cosmic collisions, we're piecing together the story of how the universe works on the grandest scales. This synergy between different types of observations is revolutionizing astronomy, offering new ways to probe the mysteries of the cosmos. Next, we'll dive into how gamma-ray bursts are helping us study the magnetic fields of the early universe, shedding light on the conditions that shape the cosmos as we know it. Now, let's shift our focus to another fascinating aspect of gamma-ray bursts: their role in uncovering the secrets of the early universe's magnetic fields. These powerful cosmic explosions act as cosmic probes, allowing scientists to study the magnetic environments that existed billions of years ago when the universe was still in its infancy. Gamma-ray bursts are like cosmic flashlights illuminating the distant reaches of space and time. As their light travels across the universe, it interacts with magnetic fields along the way. By analyzing the polarization of this light, how it's oriented as it reaches us, astronomers can infer the strength and structure of these ancient magnetic fields. This is because magnetic fields can twist and align the light waves, leaving behind a unique signature that scientists can decode. One of the most intriguing discoveries is that magnetic fields appear to have been present even in the early universe, long before galaxies and stars fully formed. This challenges some theories about how magnetic fields originate, suggesting they may have been woven into the fabric of the cosmos from the very beginning. Gamma-ray bursts provide some of the best evidence for this, as their light carries information from a time when the universe was just a fraction of its current age. Studying these ancient magnetic fields also helps us understand how they influenced the formation of galaxies and large-scale cosmic structures. Magnetic fields play a crucial role in shaping the flow of gas and dust, which are the building blocks of stars and galaxies. By tracing their origins and evolution, scientists can piece together how the universe transformed from a smooth, featureless expanse into the intricate web of galaxies we see today. What makes gamma-ray bursts particularly valuable for this research is their incredible brightness and distance. They allow us to peer back to a time when the universe was only a few 100 million years old, offering a rare glimpse into conditions that are otherwise impossible to observe. This makes them indispensable tools for exploring the mysteries of cosmic magnetism and its role in shaping the universe. As we continue to study gamma-ray bursts and their connection to magnetic fields, we're not just learning about the past, we're uncovering clues about the fundamental forces that govern the cosmos. Next, we'll explore the complex structure of gamma-ray burst jets and how they reveal even more about the physics of these extraordinary events. Now, let's turn our attention to one of the most puzzling aspects of gamma-ray bursts: the intricate structure of their jets. These jets are not just simple beams of energy. They are highly complex, with features that challenge our understanding of physics and the extreme conditions in which they form. Gamma-ray burst jets are thought to be launched during the catastrophic events that trigger these bursts, such as the collapse of a massive star or the merger of two neutron stars. What makes them so fascinating is their narrow, focused structure, which allows them to channel immense amounts of energy over vast distances. but how do these jets form and what gives them their unique shape? One leading theory suggests that the jets are shaped by powerful magnetic fields and the rapid rotation of the collapsing star or merging objects. As material is ejected at nearly the speed of light, magnetic fields twist and funnel it into narrow streams, creating the jet structure. This process is similar to how water spirals down a drain, but on a cosmic scale and with forces far beyond anything we experience on Earth. Observations of gamma-ray bursts have revealed that their jets are not uniform. Instead, they often have a layered or structured appearance, with different regions emitting energy at varying intensities. Some parts of the jet may be more energetic, while others are slower or less intense. This complexity has led scientists to propose that the jets are made up of multiple components, each with its own properties and behavior. Another intriguing aspect of GRB jets is their interaction with the surrounding environment. As the jet travels through space, it collides with gas and dust, creating shock waves that produce the afterglow we observe in X-rays, optical light, and radio waves. These interactions can also cause the jet to slow down or change direction, adding another layer of complexity to its structure. Despite decades of research, many questions about GRB jets remain unanswered. For instance, why do some jets appear to be more focused than others? And what determines the angle at which they are launched? These mysteries continue to drive astronomers to refine their models and develop new ways to observe these extraordinary phenomena. By studying the structure of gamma-ray burst jets, we're not just learning about the bursts themselves, we're gaining insights into the fundamental processes that govern the most energetic events in the universe. Next, we'll explore how gamma-ray bursts contribute to the production of cosmic dust, a key ingredient in the formation of stars and galaxies. Now, let's shift our focus to an often overlooked yet crucial role of gamma-ray bursts, their contribution to the production of cosmic dust. While these bursts are known for their explosive energy, they also play a surprising part in creating the very building blocks of galaxies and stars. Cosmic dust, made up of tiny particles of carbon, silicon, and other elements, is essential for the formation of stars and planets. Without it, the universe as we know it wouldn't exist. But where does this dust come from? One of the key sources is the aftermath of gamma-ray bursts. When a gamma-ray burst occurs, particularly those associated with the collapse of massive stars, the explosion ejects vast amounts of material into space. This material, rich in heavy elements forged in the star's core, expands outward and begins to cool. As it cools, the atoms and molecules within the ejected material start to clump together, forming microscopic grains of dust. This process is especially significant because gamma-ray bursts often occur in regions of active star formation. The dust they produce becomes part of the surrounding interstellar medium, the vast clouds of gas and dust that fill the space between stars. Over time, this dust-rich environment provides the raw materials needed for new stars and planets to form. Interestingly, gamma-ray bursts aren't just passive contributors to dust production. The intense radiation and shock waves from the burst can also trigger chemical reactions in the surrounding gas, accelerating the formation of complex molecules and dust grains. This means that GRBs don't just scatter dust, they actively shape the conditions for its creation. Scientists have observed this phenomenon in the afterglows of gamma-ray bursts, where infrared light reveals the presence of newly formed dust. These observations have helped confirm that GRBs are not just destructive forces but also creative ones, playing a vital role in the cosmic cycle of matter. By studying how gamma-ray bursts contribute to dust production, we gain a deeper understanding of how the universe recycles material from dying stars into new generations of celestial objects. Next, we'll explore the fascinating connection between gamma-ray bursts and the shock waves produced by supernova, shedding light on another layer of their cosmic impact. Now, let's dive into another fascinating aspect of gamma-ray bursts: their connection to the powerful shock waves produced by supernova. These shock waves are not just byproducts of stellar explosions. They play a critical role in shaping the universe and are deeply intertwined with the behavior of gamma-ray bursts. When a massive star reaches the end of its life and explodes as a supernova, it releases an enormous amount of energy. This energy doesn't just vanish into space, it creates shock waves that ripple through the surrounding interstellar medium. These shock waves compress the gas and dust in their path, heating it up and triggering a cascade of physical and chemical changes. Gamma-ray bursts, particularly those associated with the collapse of massive stars, are often accompanied by these supernova shock waves. In fact, the same explosion that produces a gamma-ray burst can also generate shock waves that travel outward at incredible speeds. These shock waves can interact with the material ejected during the burst, further accelerating particles and creating conditions for even more energetic phenomena. One of the most intriguing implications of this connection is how it helps scientists understand the mechanisms behind gamma-ray bursts. By studying the shock waves produced by supernova, researchers can gain insights into the processes that drive these bursts. For example, the shock waves can reveal details about the structure of the collapsing star, the distribution of ejected material, and even the magnetic fields involved in the explosion. Moreover, the interaction between gamma-ray bursts and supernova shock waves has broader implications for astrophysics. These shock waves can trigger star formation by compressing nearby gas clouds, effectively seeding the birth of new stars. They also play a role in dispersing heavy elements such as iron and nickel, forged in the supernova explosion, enriching the interstellar medium and contributing to the chemical evolution of galaxies. In some cases, the shock waves from a supernova can even amplify the effects of a gamma-ray burst. For instance, they can enhance the brightness of the burst's afterglow or create additional emission features that provide valuable clues about the explosion's environment. This interplay between gamma-ray bursts and supernova shock waves highlights the complex and dynamic nature of these cosmic events. By exploring this connection, scientists are not only uncovering the secrets of gamma-ray bursts but also gaining a deeper understanding of how supernovas shape the universe. Next, we'll turn our attention to how gamma-ray bursts help astronomers study the interstellar medium, the vast and mysterious space between stars. Now, let's shift our focus to how gamma-ray bursts serve as powerful tools for studying the interstellar medium, the vast and intricate network of gas and dust that fills the space between stars. This cosmic material, though often invisible to the naked eye, plays a crucial role in the life cycle of galaxies, and gamma-ray bursts provide a unique way to probe its secrets. When a gamma-ray burst occurs, its intense radiation travels through the interstellar medium before reaching our telescopes. Along the way, this light interacts with the gas and dust, leaving behind a kind of cosmic fingerprint. By analyzing these interactions, astronomers can learn about the composition, density, and even the temperature of the interstellar medium. One of the key ways gamma-ray bursts help in this study is through their afterglows. As the burst light passes through the interstellar medium, certain wavelengths are absorbed by the gas and dust, creating distinct absorption lines in the spectrum. These lines act like a barcode, revealing the chemical elements present in the medium. For example, elements like hydrogen, carbon, and oxygen leave specific signatures that scientists can identify and measure. Additionally, gamma-ray bursts can reveal the structure of the interstellar medium. The gas and dust are not evenly distributed. They form clouds, filaments, and voids that vary in density and temperature. As the burst light travels through these regions, it encounters different conditions which affect how the light is absorbed and scattered. By studying these variations, astronomers can map the complex structure of the interstellar medium in unprecedented detail. Another fascinating aspect is how gamma-ray bursts help us understand the role of dust in the interstellar medium. dust particles, though tiny, can significantly affect the light passing through them. They absorb certain wavelengths and scatter others, creating a phenomenon known as extinction. By observing how gamma-ray burst light is dimmed and reddened by dust, scientists can estimate the amount and properties of dust in different regions of space. This information is invaluable for understanding how stars and planets form. The interstellar medium is the raw material from which new stars and planetary systems are born. By studying its properties, astronomers can gain insights into the conditions that lead to star formation and the processes that shape the evolution of galaxies. Gamma-ray bursts also provide a way to study the interstellar medium across vast distances. Because these bursts are so bright, they can be observed even in distant galaxies, allowing scientists to compare the properties of the interstellar medium in different parts of the universe. This helps us understand how the medium has evolved over cosmic time and how it varies from one galaxy to another. In essence, gamma-ray bursts act as cosmic flashlights, illuminating the hidden corners of the universe and revealing the intricate details of the interstellar medium. By studying these bursts, astronomers are not only learning about the material that fills the space between stars, but also gaining a deeper understanding of the processes that drive the evolution of the cosmos. Next, we'll explore the characteristics of galaxies that host gamma-ray bursts and what they tell us about the conditions necessary for these powerful cosmic explosions. Now, let's turn our attention to the galaxies that serve as the birthplaces of gamma-ray bursts. These host galaxies are more than just cosmic backdrops. They hold vital clues about the environments that give rise to these extraordinary explosions. By studying these galaxies, astronomers can piece together the puzzle of what makes a galaxy capable of producing such powerful bursts of energy. One striking feature of gamma-ray burst host galaxies is their star-forming activity. Many of these galaxies are bustling with the birth of new stars, often at rates much higher than those seen in more tranquil galaxies like our Milky Way. This intense star formation suggests that gamma-ray bursts are closely tied to the life cycles of massive stars, which live fast and die young in spectacular supernova or neutron star mergers. The abundance of young, massive stars in these galaxies creates the perfect conditions for gamma-ray bursts to occur. Interestingly, not all host galaxies are the same. Some are small, irregular galaxies with chaotic structures, while others are larger, more organized spiral or elliptical galaxies. This diversity tells us that gamma-ray bursts can happen in a wide range of galactic environments. However, one common thread is that these galaxies often have lower levels of heavy elements or metallicity compared to galaxies like ours. This lower metallicity may play a key role in allowing massive stars to retain enough mass to eventually collapse into gamma-ray bursts. Another intriguing aspect is the location of gamma-ray bursts within their host galaxies. Observations show that these bursts often occur in the outer regions of galaxies, away from the dense central areas. This could be because the outer regions have fewer heavy elements, which, as we've seen, might be crucial for gamma-ray burst formation. Alternatively, it could be due to the fact that massive stars in these regions are less likely to lose their outer layers through stellar winds, preserving the conditions needed for a powerful explosion. By studying the properties of these host galaxies, astronomers can also learn about the broader cosmic environment. For example, gamma-ray bursts in distant galaxies provide a window into the early universe when galaxies were younger and less chemically evolved. Comparing these ancient host galaxies to those in the nearby universe helps scientists understand how galaxies and their star-forming processes have changed over billions of years. In essence, gamma-ray burst host galaxies are like cosmic laboratories, offering a unique glimpse into the conditions that lead to these extraordinary events. They reveal the intricate interplay between star formation, metallicity, and galactic structure, shedding light on the factors that make a galaxy capable of producing one of the universe's most energetic phenomena. Next, we'll delve into how gamma-ray bursts serve as cosmic clocks, helping astronomers measure the passage of time across the vast expanse of the universe. Now, let's explore how gamma-ray bursts act as cosmic clocks, offering astronomers a unique way to measure time across the vast expanse of the universe. These powerful explosions, occurring billions of light-years away, provide more than just a glimpse into the universe's most energetic events. They also serve as precise markers of cosmic time. Gamma-ray bursts are incredibly bright and short-lived, making them ideal for studying the universe's timeline. When a burst occurs, its light travels through space and time, eventually reaching Earth. By measuring the time it takes for this light to arrive, astronomers can calculate the distance to the burst and in turn determine how long ago it happened. This allows gamma-ray bursts to act as cosmic stopwatches, helping scientists piece together the history of the universe. One of the most fascinating aspects of using gamma-ray bursts as timekeepers is their ability to probe the early universe. Because these bursts can be detected from such immense distances, they provide a way to study events that occurred when the universe was just a fraction of its current age. For example, the light from the most distant gamma-ray burst has been traveling for over 13 billion years, offering a direct look at the universe's infancy. This makes them invaluable tools for understanding how the cosmos has evolved over billions of years. Another key feature of gamma-ray bursts is their consistency. While each burst is unique in its energy and duration, the underlying physics of these events is well understood. This consistency allows astronomers to use them as reliable benchmarks for measuring cosmic distances and time. By comparing the properties of different bursts, scientists can create a timeline of the universe's expansion and map out how galaxies and other structures have formed and changed over time. Gamma-ray bursts also help astronomers test theories about the universe's rate of expansion. By observing how the light from these bursts stretches and shifts as it travels through space, a phenomenon known as redshift, scientists can measure how fast the universe is growing. This information is crucial for understanding dark energy, the mysterious force driving the universe's accelerated expansion. In essence, gamma-ray bursts are more than just cosmic fireworks. They are precise tools that allow us to measure the passage of time on a universal scale. By studying these bursts, astronomers can trace the history of the cosmos from its earliest moments to the present day and gain deeper insights into the forces shaping our universe. Next, we'll look ahead to the future of gamma-ray burst research, exploring the cutting-edge technologies and missions that promise to unlock even more secrets about these extraordinary cosmic events. As we look to the horizon of gamma-ray burst research, the future holds incredible promise for uncovering even more secrets about these cosmic explosions. New missions and advanced technologies are set to revolutionize our understanding of gamma-ray bursts, offering unprecedented insights into their origins, behavior, and impact on the universe. One of the most exciting developments on the horizon is the launch of next-generation space observatories. Missions like the European Space Agency's Athena and NASA's Lynx X-ray Observatory are designed to study gamma-ray bursts with greater precision than ever before. These observatories will be equipped with cutting-edge instruments capable of capturing high-resolution images and spectra of gamma-ray bursts, allowing scientists to analyze their properties in exquisite detail. With these tools, researchers hope to uncover new clues about the environments where gamma-ray bursts occur and the mechanisms that power them. In addition to space-based observatories, ground-based telescopes are also playing a crucial role in advancing gamma-ray burst research. Facilities like the Vera C. Rubin Observatory and the Cherenkov Telescope Array are set to provide complementary observations in optical and gamma-ray wavelengths. By combining data from these telescopes with observations from space, astronomers can create a more comprehensive picture of gamma-ray bursts from their initial explosion to their lingering afterglows. Another area of innovation lies in the development of multi-messenger astronomy, which combines observations of gamma-ray bursts with other cosmic signals, such as gravitational waves and neutrinos. This approach has already yielded groundbreaking discoveries, such as the detection of a gamma-ray burst coinciding with a neutron star merger in 2017. As detectors for gravitational waves and neutrinos become more sensitive, scientists anticipate even more opportunities to study gamma-ray bursts in conjunction with these signals, shedding light on the extreme physics at play in these events. Artificial intelligence and machine learning are also transforming the way gamma-ray bursts are studied. These technologies enable researchers to sift through vast amounts of data more efficiently, identifying patterns and anomalies that might otherwise go unnoticed. By automating the analysis of gamma-ray burst observations, scientists can accelerate the pace of discovery and uncover new insights into these enigmatic phenomena. Looking further ahead, ambitious projects like the Laser Interferometer Space Antenna, or LISA, aim to detect gravitational waves from gamma-ray bursts and other cosmic events with unprecedented sensitivity. This mission, set to launch in the next decade, could open a new window into the universe, allowing us to observe gamma-ray bursts in ways we've never imagined. The future of gamma-ray burst research is not just about new technologies, it's also about collaboration. International partnerships between space agencies, observatories, and research institutions are driving progress in this field, pooling resources and expertise to tackle some of the most challenging questions in astrophysics. Together, these efforts are paving the way for a deeper understanding of gamma-ray bursts and their role in the cosmos. As we continue to explore these cosmic explosions, one thing is certain: gamma-ray bursts will remain at the forefront of astrophysical research, offering a unique lens through which to study the universe's most extreme events. With each new discovery, we move closer to unraveling the mysteries of these powerful phenomena and the universe they illuminate. As we wrap up our journey through the 50 incredible facts about gamma-ray bursts, it's clear that these cosmic explosions are more than just fleeting flashes of light in the universe. They are powerful windows into the most extreme environments and events, from the birth of black holes to the collisions of neutron stars. Each burst tells a story of unimaginable energy, ancient galaxies, and the fundamental forces that shape our cosmos. Through gamma-ray bursts, we've glimpsed the early universe, tested the limits of physics, and uncovered clues about the origins of heavy elements like gold and platinum. These phenomena remind us that the universe is a dynamic, ever-changing place, filled with mysteries waiting to be unraveled. But the story of gamma-ray bursts is far from over. With every new discovery, we're reminded of how much we still have to learn. What other secrets do these cosmic explosions hold? Could they help us unlock the mysteries of dark energy or the nature of space-time itself? The answers lie in the data yet to be collected, the missions yet to be launched, and the minds yet to be inspired. So, as we close this chapter, let's keep looking to the stars with curiosity and wonder. What will the next gamma-ray burst reveal about the universe and about us? If you're as fascinated by these cosmic mysteries as we are, don't forget to hit that subscribe button, like this video, and ring the notification bell to stay updated on the latest discoveries. The universe is full of surprises, and we can't wait to explore them with you. Until next time, keep wondering, keep exploring, and keep reaching for the stars.